Cool. Yeah, I think we're ready to start then. Hopefully everyone on Zoom can hear us as well. And yeah, let's start sharing the screen. Cool. So yeah, just wanted to do a bit of an introduction first. Obviously, thanks everyone for coming. I know it's quite early in the morning, so hopefully no one's too jet lagged. But yeah, I just wanted to go a bit over the schedule. So obviously starting off with the introduction, we're then going to have one of the keynotes from Oshin Moke. And then the rest of the first block of the workshop will be discussing the challenge. So a bit about what the setting is, what kind of some of the summaries in terms of the results that we got were. And then we have two presentations by the challenge winners. So one from the self-supervised track of the challenge and one from the supervised track. We'll then have a half-an-hour break, which also aligns with the kind of CVPR breaks. I don't know where the breaks actually are, but I'm sure there'll be people to help around. And then we have the final two keynotes from Daniel Kremers and Alex Kendall. So yeah, that's pretty much it. Probably not much to discuss, but if anyone has any questions now, just before we start, then feel free to shout out. Cool. So hopefully that's also still screen sharing the correct one. And yeah, just go quick. So yeah, so our first keynote is Oshin Moke, who's a lecturer in machine learning in the School of Informatics at the University of Edinburgh. From 2016 to 2019, he was a postdoc in Professor Pietro Perona's Computational Vision Lab at Caltech. And prior to that, he was a postdoc in the Department of Computer Science at UCL with Professor Gabriel Brosto and Professor Kate Jones. He received his PhD from UCL in 2014, advised by Professor Gabriel Brosto, and he has an MSc in machine learning from UCL and a BEng in electronic and computing engineering from the University of Galway, along with being a fellow of the Alan Turing Institute and an Ellis Scholar. His current research interests are the areas of computer vision and machine learning, with a specific emphasis on shape and depth estimation, human-in-the-loop learning, and fine-grained image understanding. Yeah, thanks a lot. Can I get a quick confirmation from Zoom if it's sharing the advancing monocular depth estimation slides?
No, we can see questions from the old slides.
Cool. Cool. So hopefully you should be able to see it now.
I think we're seeing not the right view of it.
Which, it should be. Desktop one. Yeah, I guess that's probably the easiest. How about now?
Yeah, now it looks right.
Cool, great.
Great. Cool. Okay, thank you so much, Jamie, for the introduction. Can everyone hear me okay? Yeah, perfect. Okay, cool. So yeah, thanks so much everyone for getting up pretty early in the morning to come hear me talk. So I really appreciate it. I'm going to talk today about monocular depth estimation, some work that myself and some of my collaborators have been doing. I'm also going to try and talk a bit about what I think are kind of maybe still open challenges in the space. So it'll be cool to kind of maybe engage in a bit of discussion after the talk as well about whether you agree with me or whether you disagree with me. Does anyone actually not know what monocular depth is? I'm guessing this audience probably is pretty familiar with it, yeah? Okay, great. Well, that makes my life a bit easier. Okay, so let's say I have this photograph. I'm taking this from Wikipedia. This is a photograph from Vancouver from the 1940s. And so with an old photograph like this, we can't go back and put a LiDAR scanner in. We can't go back and take multiple images of that scene. So if we want that depth from that from an image like this, really we have to rely on monocular depth methods. And so if we take an off-the-shelf monocular depth method, what we get here is a per pixel labeling, you could think of it. What we're getting is a continuous value for each pixel representing the distance or depth of that pixel from the camera. And so if I flick back and forth, you can kind of see here in this example that the brighter pixels are closer to the camera and the darker pixels are further away. And so this example here, it's done a pretty good job of this image. You know, you can kind of see some of the detail like the cars and the legs of the people and so on. Maybe it's not fantastic on the projector here, but you can get a sense that it's actually doing a pretty reasonable job. Okay, so what about humans in monocular depth? So the kind of cool thing is that there's a whole bunch of different cues that we actually use to be able to perceive depth in images. So, you know, if I cover one of my eyes, I'm still actually going to be able to do a pretty good job of perceiving the distance to objects in the world. And the same obviously holds for when I'm holding a photograph and I don't have any kind of motion cues or stereo cues. And so in practice, you know, as humans, we're using a whole bunch of different information and kind of fusing that together. So that ranges from things like occlusion of objects, maybe relative size, if we have some prior about the size of an object and we see differences, but also the shadows that objects cast on the ground, maybe shading cues. We might expect to see light on top of objects and maybe darker things underneath, distance to the horizon, you know, perspective. All these cues are basically integrated together and allow us to perceive depth. Is monocular depth useful? Again, probably this audience, I'm guessing, would agree, but there's a whole bunch of applications that we can use monocular depth for. So that might be human-computer interaction. So the paper from a few years ago that's doing hand pose estimation, which is aided by depth here from a Kinect sensor. But we can also do things like relight images. So if I have depths, I can do things like compute normals, and then I can actually relight the scene by placing virtual objects or virtual lights into the environment. More recently, we've seen kind of amazing progress on conditioned image synthesis. So here's an input image, and here's predicted depth from Midas. And so we can drive the generation of new images based on the structure imposed by the depth. So this is quite cool because basically what's being enabled here is we're getting the same type of structure in terms of the distance from pixels or relative distance from pixels to the camera, but we're changing the appearance of it. So this is actually quite a powerful way to generate new images while still imposing some relatively strong priors about what you want the structure of the scene to look like. And this is a really nice, I think, fun example of that. People might have seen this already. So basically, in this example, the person has taken these little toy furniture pieces, like a bed and table and so on, predicted the depth first, and then they've synthesized new examples from based on that depth using kind of off-the-shelf diffusion models. And so you can actually go, I guess maybe you can check out that example online because it's a really cool little animation where they just generate a whole bunch of examples. Augmented reality, this is another one I'm going to touch on a bit today at some point in my talk. But basically, if you can imagine scenarios where we want to place virtual characters into the world, if we don't have depth, effectively all we're doing is just pasting these pixels onto the image. And if you observe closely here, you'll observe that basically the object doesn't get occluded by any objects in the scene. So it doesn't look particularly immersive. In practice, so here on the right, we're actually going to use an estimate of depth for each pixel and some other things, but that allows us to actually respect the occlusion boundaries from real objects in the world and kind of enhances the immersion. We can also use depth, monocular depth, to generate training data. And so we've done this in the context of stereo training. So we can take an image collection like Coco ImageNet. We can compute monocular depth from each image in that data set. Then we can render each image from a slightly different viewpoint using the appearance from the input image and the monocular depth. And actually then effectively what we've done is we've generated pairs of stereo training data. And so it's going to be imperfect and limited by the quality of the monocular depth, but in practice, it allows us to generate much more visual diversity and examples, which we can then do to improve our stereo training. So it's kind of a simple trick that works quite well. You know, the cool thing about depth, I think, is now it's become this kind of building block in other kind of pipelines. So here's an example from one of my PhD students, Mehmet, at Edinburgh. So he's interested in the problem of a 3D object reconstruction from just single image collections. So again, let's say I took the horse category or the elephant category on ImageNet. I don't have multi-view data, but what I can do is just use off-the-shelf segmentation and off-the-shelf monocular depth. And then with some kind of smart analysis by synthesis methods, we can basically generate 3D models from those image collections. And those can also be articulated as well. So depth there is kind of like a building block in this pipeline. Okay, so I guess I'll do kind of a brief overview of how we actually compute depth. But again, I think for this audience, people are going to be pretty familiar with this. So pre kind of the deep learning era, there was a whole bunch of pretty influential work on monocular depth estimation. So those were papers like automatic photo pop-up, which did things like, enforced some priors or structural priors about the types of relationships we expect to see between surfaces and real scenes, and that allowed them then to generate these kind of semi-plausible 3D renderings of images from different viewpoints. Subsequently, that we saw kind of more work that used more actual explicit machine learning in this pipeline, and so doing things like breaking scenes up into local regions using kind of over segmentation and super pixels, and then inferring something about the relative position of those pieces, and then doing kind of global optimization. They were able to again do a pretty good job on actually generating depth estimates or pseudo depth estimates for these scenes. But these were not kind of, as we think of it now, kind of end-to-end pipelines. They were kind of quite carefully designed systems. In the deep learning era, the problem in some sense became a lot more simplified, or at least some of the early approaches to do this. It's basically like a pixel labeling problem. So we can just treat this as a supervised learning task. So we've got some input frame, we've got some deep network, I guess, kind of indicated by that little hard to see arrow. And what we'd like to be able to do is predict some depth that looks like our supervised ground truth. So this is a kind of a standard supervised paradigm. We have some supervised data, we train our model, let's say, for example, some kind of UNet-like structure, so that we can estimate this continuous value for each pixel, and we just put a squared error on that and train that model. So assuming we have enough data, this is actually, a pretty reasonable thing to do, and you can get quite far by just doing that alone. And there's been amazing work in this space. Maybe even people here have worked on this problem. And so this is just one example method. This is Midas from a few years ago. And combining deep networks, lots of supervised data and diverse data sources. So in their case, from movies, they were using stereo movies. They actually have, pretty impressive results, and people have been building on this method. And there's these are kind of like the building block of a lot of the examples I showed earlier on, like the image synthesis based pipelines. Okay, but what's the challenge here? So one of the challenges is the sources of depth supervision. So in the supervised case, we need to get supervised data, and so if we're relying on kind of physical devices to do that, those devices, they're heavy, they're expensive, things like LiDAR scanners. They also have limited maybe depth range. They're also just going to have difficulties operating in certain types of scenarios, like underwater, for example, but also in bright sunlight. Sometimes they're going to be sparse. They can't handle moving scenes. So there's just a whole host of limitations that make this challenging. And so a question that we set out to think about a few years ago now at this stage was actually, could we train these monocular methods without ground truth depth supervision, just with self-supervision alone? Yeah, and so we did this by making use of stereo data. Okay, so again, in a stereo setting, we have two frames taken of the same scene at the same point in time. And so again, you can think of this as two cameras imaging the scenario. And if we're able to triangulate those points, so if we know where a point each pixel is, for example, in the left image, or we know it is in the right, as long as we know the relative transformation of the cameras, we can actually estimate the disparity and turn that into depth. So in a sense, stereo allows us to take pairs of images, turn that into depth. And so the key trick here in the self-supervised paradigm is, how do we make use of this type of data to train a model that can then predict depth from just a single image alone? And so there's our kind of estimated depth in the stereo setting. And so the trick here is to just view this as an image synthesis problem during training time. So the idea is that if I took that input image in the top left, if I had the correct depth, I should be able to then generate that scene from different viewpoints. And so in a sense, basically what I can do is I can synthesize one of the other viewpoints from the input image and the estimated depth. And as long as I'm able to correctly estimate the depth, basically I should be able to reconstruct that image under the assumption that the scene is static. There's no large scale illumination or appearance differences based on the changes in viewpoint. And so we turn this depth estimation problem into an image reconstruction one, or an image synthesis one, if you like, by imposing some specific structure and the sampling process of the image during the reconstruction phase. Okay, so this is cool because actually we don't need supervised data anymore. We can just use stereo images at training time, but we still only need a single image at test time. So that's the cool thing about it. Effectively, our model is just going to take that image as input, estimate the depth for us, and we can handle moving objects because we're getting two images at the same point in time. But the downside is that we require temporally aligned stereo pairs, and obviously just occlusion, just because some pixels are going to be visible in one image and not the other. That's going to be a problem. So building on this, a whole bunch of people, and this has become a whole kind of area of work, have started to think about how do we actually train without stereo supervision? So how do we train these types of self-supervised methods without stereo supervision? And the cool potential here is obviously that this would just unlock a huge resource of data that's available to us. You know, we could just go online and download these videos, and we'd have an amazing source of kind of visually diverse, interesting scenes, different scenarios that we could train our model on. So this would be, in some sense, the holy grail of being able to just take, you know, unconstrained large collections of videos and being able to train on that to estimate depth. Okay, so maybe I'll talk about this for a minute, and just as a primer. So again, in our stereo setting, we've got stereo pairs at different time steps. So 3 time steps here on the left. And in the monocular setting, we only have the single camera. So what we did in the stereo setting, obviously, is we knew something about the baseline between the cameras. We didn't actually use the temporal data at all. In the monocular setting, we don't have pairs, we just have the sequence, and so we're going to have to infer something about the relative pose between frames in the sequence. And so the pipeline is actually very similar. All that we've done here is change the frames that we use. So we use the frame at the current time point, and then we use a frame at a different time point. So instead of stereo pairs, we just use temporal pairs. And because we don't know the actual transformation between the cameras, we have to estimate that online. So that's our little pose prediction network down the bottom right corner. And so in a sense, we're still doing the same thing. We're just trying to estimate the depth so that we can reconstruct a frame in the video, but we're going to have to estimate pose as well at the same time. And so this is work SFM Learner, probably many people know this from CV4 2017, and then we built on this ourselves in this monodepth 2 method a few years later, kind of adding some additional components to overcome some of the challenges of doing this well. And again, just to get a sense of what the pose network looked like, we're just basically taking a pair of images and producing a prediction of the transformation, and the rotation, and translation and rotation. And so that's down at the bottom right here. Great. Okay, so this is kind of where we were all at. I think as of a few years ago. So monodepth for 2017 was one of the earlier stereo-based methods, and that's an example of a prediction on the test scene. So we have some input image. Here's a prediction of the estimated depth with brighter colors indicating closer to the camera. Then SFM Learner came along and kind of did this amazing thing of removing the constraint of having to need stereo pairs and just training on single image sequences, but the quality of the predictions was not as good. And this was our monodepth 2 method at the time, which kind of enhanced that performance, or enhanced the prediction quality when training on just sequences. And then, as maybe many people know here, there's just been an amazing amount of work previous to that and following that on this problem, and we've seen kind of a really impressive performance on some of the real challenging components of this problem. Okay, so those kind of challenges are things like, as we move through an environment, we're going to have occlusion. So some things are going to appear and disappear. So when we make these assumptions about being able to reconstruct later frames based on current frames and estimated depth, that's going to break down in certain situations because pixels just aren't visible anymore. And we've also got problems like objects that move at the same velocity as the camera. So that's a real pain because from the camera's point of view, or from the method's point of view, we could also just represent those as kind of infinitely far away objects. And so we have to deal with these kinds of challenges. Okay, but there's all the pros. We don't have to require supervised data. We don't need stereo data, and we don't need pose. We just estimate pose, and we only need to do that at training time as well. But this is sensitive to moving objects. It does require that the camera is actually moving. It's no good just having a static scene and a static camera. And we require reasonably well-behaved cameras. I mean, I think to some extent that's been a lot of the secret behind the performance we get on data sets like Kitty is basically we don't have a particularly challenging camera. We just have this camera moving nice and smoothly through the environment, typically always moving in a forward direction. And so that's a lot easier than actually walking around with a really challenging set of poses that you have to try and deal with. And so, you know, people are working on this and we're getting kind of improvement, but these are some of the reasons why this stuff actually worked in the first place. Okay, so I want to talk a bit about a paper we worked on, I guess 2 years ago at this point, which was addressing a kind of an obvious question that arises in the context of monocular depth estimation. So yes, we want to have methods that just take a single image as input and predict the depth, but actually in practice, we also often have multiple frames at test time. And so how can we use those multiple frames when they're available to do a better job of estimating the depth? Okay, so again, harking back to the methods we talked about a second ago, when we just have single images, we just have an input image, we have our network here in this kind of yellow box, and we make our prediction. But in practice, self-driving scenario is a good one. We might actually have multiple frames available to us, and so we'd like to be able to use those. And so there's been a whole bunch of work on this problem, and there's been work subsequently as well. So one way you can do this is via test time refinement. And so this is kind of an obvious but kind of cool outcome of the self-supervised paradigm, in that we can just do the same thing we did at training time at test time, because we didn't need any supervised data. We can basically just refine the models on the test sequences that we have. Well, the problem is that that's expensive, so because we have to do actual optimization to do that. The other types of things that people do is that we could actually impose some kind of structure in the bottleneck of our model, and we can actually model then some kind of temporal coherence, or basically model the temporal nature of this. So, for example, you could imagine having like a recurrent network that's just making use of information from the previous time step. Well, the problem here is that this doesn't explicitly actually encode any specific geometric constraints. And then the other approach would be kind of a more classic kind of multi-view stereo type of approach. But those methods at the time of when we worked on this problem, they were generally supervised. They couldn't handle moving objects, or they couldn't handle situations where the camera was static. So what we'd like to have instead is a network that can take a single frame as input, as we see in the top right, and make a prediction. And you can kind of see the error maps below the depth prediction, but also with the exact same network, still be able to take multiple frames in if they're available, and hopefully improve the performance of the depth estimate. And so that's kind of realized there by the fact that we see more bluer colors in the image, which indicates that there's less errors. Yeah, so that's our mani-depth method. So it's self-supervised, that it only requires video sequences for training. It's real time because it's only just a single forward pass through the network. And it works for both single or multi-frame settings, depending on what you have. But it also works in cases where the traditional multi-frame ones don't, like the static cameras, and to some extent it can handle moving objects. Great. Okay, so again, the monocular depth framework, as we're used to seeing it, single image network, it predicts the depth. If we just naively added a cost volume, so I won't get into today what a cost volume is, but many of you might already know that kind of from multi-view work. But basically, if we just added a cost volume, we can do this, but what I'll show you later on is that this is basically going to fail in very specific situations, which hinders our ability to kind of use it naively. The advantage of a cost volume is, again, we can just use this cost volume. We can effectively test what the depth would be like for different values, different VEP values, and then we can use simple 2D convolutions on top of this cost volume, so we don't have to do any expensive 3D convolutions and still get and still keep this thing nice and efficient. But again, there's a problem that this tends to fail. And so there's a couple of reasons why this doesn't work. So one is a problem called cost volume, or what we call cost volume overfitting. Another is that when we in a self-supervised setting, we don't actually know anything about the constraints of our scene. We don't know what the minimum maximum depth is. We don't know what the scale of the depth is. And so cost volume methods typically require us to set those kind of hyperparameters when we're building the volume. And so we're also going to encounter test frames where there's no baseline. So you can imagine, again, a car sitting at a traffic lights, there's no motion, and so the cost volume methods are going to basically break when you do that. Yeah, and so if you just naively introduce a cost volume, it actually performs pretty terribly. So this would be an example of a single frame prediction. And the bottom is an example of a method just naively using a cost volume. And you can see that it's, hopefully you can see that it's doing kind of a terrible job on those cars there. It's predicting them at infinite depth or minimum disparity. And this kind of makes sense when you look at it here, because when we look at the actual cost volume, so we just look at the argmin of the cost volume, so i.e. the best match, you can see that basically the problems that are introduced in the cost volume are basically just replicated in the network output. And those problems are things like, again, cost volume can't handle moving objects, can't handle a low texture, and then just appearance issues in the scene like lens flare and all those kinds of things are also problematic. So the idea that behind the many-depth method is actually quite simple. We just effectively use the best of both worlds. So we can see that the single image networks, they suffer far less on those types of moving objects. And so in some sense, we should just trust those predictions from the model. And similarly, the multi-view, the cost volume-based approach works actually quite well, you know, in the situations it's designed for, and we should trust it in those situations. And so effectively what we do is we generate a mask, which allows us at training time to decide which source of self-supervision we should trust. And so you can see that mask down on the bottom right there. And so you can see the mask is basically telling us, don't trust the cost volume on the car or the sky, but other places you should actually trust it. Okay, so I kind of zipped through that a bit quickly, but happy to talk about it offline if people have questions. But the high level takeaway here is that we're then able to overcome some of these challenges of naively using cost volume. We still get an efficient single pass method, a single forward pass, and it does a better job of these kind of traditional LSTM type methods that existed at the time. And so that's what we're seeing on the right here. So this is our approach down the bottom, and you can see that there's more blue pixels in the sense that there's less errors in comparison to some of those other types of approaches. Okay, and so this is just a visualization of the fused depths for a sequence from Kitty, and you can see here kind of that it does a pretty reasonable job just through naive fusion of predicting the structure of the scene. Okay, so building on that, we have this kind of building block now of monocular depth, and I want to talk for a few minutes about the kinds of things we can do with monocular depth, or the kinds of things we've been doing with it. And one of them is actually, can we use estimated depth for efficient 3D reconstruction? So what I mean by that is we like to take a collection of images of a scene, imagine a room like this, and I'd like to be able to get a full dense 3D reconstruction of that environment. The key difference of this approach that I'll briefly talk about, and this is a paper that we presented at WACV, was instead of trying to represent the scene as a dense 3D structure, instead we're just going to represent it in this kind of simplified 2D way. So effectively what we're going to do is for each pixel in the scene, we're just going to represent the height that pixel is off the ground. So that makes a simplifying assumption that all objects can be represented by a single height. So like a table is a good example where that breaks because it has an underside and a top side, but actually a lot of man-made scenarios can be reasonably assumed to have this type of structure, or certainly for types of, let's say, navigation purposes where you just want to walk around things. Okay, and so I won't get into the details today, but the high-level takeaway is that we can use depth estimated from methods like our many-depth and actually fuse them together using a TSDF type representation, and then just representing the height of the depths in that scenes, and introducing another network that can then kind of in some sense clean up those mistakes. We can have much better, higher quality representations of these scenes without actually having to do expensive full 3D convolutions and keeping track of 3D features and so on. And again, just to give you a sense of what that looks like for some scenes here from ScanNet, you've got basically the ground truth in the middle, and then we've got our prediction here on the right. And we can see in this animation what this kind of looks like over time. So effectively, we're fusing these predicted depths into a top-down representation, and then being able to kind of extract out a 3D structure from that just encodes the height of objects in the scene. Great. Okay. And so let me just quickly also highlight one more piece of work. And this is actually a paper that we're presenting at CVPR this week. So again, I'll just give a kind of a high level overview of that. But hopefully, if you have time, maybe some of you could come along to the poster and have a look at it as well. So the nice thing about having these kind of 3D reconstructions of scenes like we showed a second ago is then we can do things like we can actually insert virtual objects into the scene, and we can respect the actual distance that those objects would be from the camera by taking into account also any occlusion that might happen as a result of objects in the scene. And so again, the setup here of this problem is that we'd like to be able to do this in an even more efficient way. So the setup is that we have input images from some sequence. We've got some virtual object that we'd like to paste into that world. So this is like the example I gave at the very start. But we'd like to make sure that we paste it into the scene so that any objects that would be in front of it are also displayed appropriately. And you could think that the kind of conventional pipeline for this would be we have some input images, we have some virtual asset here that we'd like to render, and we've got the depth of that asset, which is shown in the middle. So we know how far we'd like it to be actually away from the camera. And the conventional pipeline would just be estimate the depth, okay, just using a standard binocular or even a multi-frame method if you have it. Test each pixel to see which is closer to the camera, the real scene or the virtual object, and effectively generate a mask from that. And then we can just composite the virtual object into the scene. You can kind of see it up here on the right, or just about, because we know which pixels should be visible or not from the virtual object. And in the paper we're presenting at CVPR, we have an alternative way of doing this, which actually circumvents the kind of traditional approach of estimating this continuous value. And instead, we just treat this as basically a binary prediction problem for each pixel. So we test each pixel to see, is this pixel visible from the camera at this particular depth? So it turns out to be a much more efficient way of doing this. But it's also great because it then allows us to introduce very simple ways of doing kind of temporal smoothing in the same pipeline in a way that just doesn't work, or we show in the paper doesn't work for traditional depth-based methods. And again, to give you a sense of what that looks like, so this pink thing represents the mask of the virtual asset that we'd like to insert into the scene. And you can see on the top, without kind of temporal smoothing, there's parts of the object that are just sometimes visible and sometimes not visible behind the chair. And when we do our temporal reasoning, we can actually, our temporal smoothing, we can actually have a much more visually consistent prediction. So let me skip this depth estimation. And so there's a whole bunch of other examples on our webpage that do a better job of kind of reflecting the quality of what this looks like, and certainly in comparison to existing kind of more standard depth-based methods. Okay, so that was a bit of a whirlwind tour, I suppose, of some of the work we've been doing on monocular depth estimation and making use of monocular depth estimation. I want to spend the last couple of minutes just talking about what I think are the current limitations for making more progress on this problem. And again, this is the kind of stuff I'd love to chat about at any point during the week if people are interested as well. Okay, so some of the obvious limitations that I think many of you probably will agree with is just the benchmark data sets that we have. We have data sets like Kitty, which are fantastic, and they've served an amazing purpose for what they were able to allow us to achieve. But, you know, they have problems. There's simple scenes, limited variation, and so on. There's things like NYU depth v2, which is great because it's indoors. But again, you know, the quality of the depth is not great. The quality of the scenes, the images are not particularly great quality. We've got the data set from the competition here, which is great because the depth is just such high quality. You've got indoor-outdoor scenes, which is amazing, but also you just have static scenes. So that's just kind of the limitations maybe of some of the acquisition setup that you have. So again, this is definitely pushing things in the right direction in terms of quality, but there's just always inherently going to be limitations. There's also data sets like depth in the wild. I don't know if people remember this paper from several years ago. So they just got humans to go in and actually annotate the relative depth of pixels in an image, which is kind of a cool way to do this. But obviously, you only get sparse annotations. You have manual annotations as well, so it's not objectively, you know, estimated by some device. And then we've got things like the sources of data that train MIDA, so just basically stereo movies, but they have problems because often that stereo is not actually captured from pairs of images, but it's instead generated by kind of humans in the loop who are doing a lot of tweaking to generate that stereo for watching movies, not necessarily for reflecting the true depth of objects in the scene. So that's data sets. I mean, another problem, and again, this is, one that is actively under extensive research, and it's one I think that self-supervised methods suffer slightly more from, is just generalization. So we can train on self-driving type scenes, but then if we take those same methods and apply them to indoor settings, they typically don't work very well. So we need to have diverse training sources of data that will allow us to overcome some of these domain gap problems. Moving objects are obviously also just a big issue for self-supervised methods. Obviously, there's been a whole bunch of work on using kind of semantic predictions to basically mask out the kinds of things that tend to move. And there's been a whole bunch of other work on trying to estimate motion models for objects in scene, but this is still a kind of an active problem. Thin structures, I think, are still quite a challenge for self-supervised methods. And temporal stability, again, is a challenge, although, again, obviously, it is something that's under a lot of extensive work. And I think, for me, what's appealing is that self-supervised learning has so much promise, but actually, we're still at a point where conventional supervised training is just so much more effective. And so really, I think the open question here is, how do we realize the potential of self-supervised training in the context of monocular depth? But supervised methods are not perfect. I mean, I don't know if anyone has kind of played around a lot with some of the more recent depth estimation methods. They're amazing, but they still have problems. So, here's a kind of a relatively tricky scene where we've got this kind of metal object with multiple holes in it. Probably not super clear on the screen here, but basically you can see that it really doesn't predict those holes in the right. This is like a hard setting. So this is like reflections. I don't know what you're supposed to do in this scenario, but certainly this is the type of thing that's going to break these methods. This is one that's actually kind of not actually particularly hard, certainly for humans, but one that still seems to be kind of tricky for these methods. So just the types of scenes that are not present in the training data clearly cause problems. And so this looks potentially like a simple setting. So we've got the legs on an elephant. And so the right back leg should obviously be further away than the left back leg, but the predictions we get here in this particular example from Midas keeps them at the same depth. And this is definitely problematic in situations where you want to use this type of output for doing things like 3D reconstruction. Again, glass, these types of things are challenges, and they're just going to cause problems for evaluation. Okay, so this is, I don't know if people have seen this, but this is actually quite cool, I think. So, I talked about this promise of self-supervised learning and where that can actually bring us. And so an open question, really, I think that's been explored a bit in the context of more general scale self-supervised learning is, does depth emerge from large scale self-supervised training? So I don't mean the kinds of self-supervised training I've talked about today, where we've imposed explicit structure on the scene to explicitly actually get depth out. But I mean more conventional kind of contrastive or self-supervised representation learning methods like Dino V2 or even CLIP to some extent. And so this is an image grabbed from the Dino V2 paper. And so what they're showing here is basically they take the method that's just been trained on their kind of standard their standard objectives, which is more designed for learning kind of semantic aligned representations. They take those features for each pixel, they freeze the model, and then they just train a linear regressor effectively on each of the local representations. And you can see that Dino here on the right, again, maybe not super clear on the projector screen, but it does actually a surprisingly effective job at actually predicting depth for these scenes. Even though this thing has not been trained at all to do, or let's say the backbone has not been trained at all to do any form of depth estimation. Clearly, this is still a supervised method because we need supervision to actually extract this out, but it's doing a pretty impressive job. Okay, so that is actually kind of really the last thing I want to talk about. So I only mentioned this in passing along the way in the sense that I showed some of the authors who were responsible for this, but definitely want to give a big thanks to all my co-authors who've really led the charge on this. So for Clement, for example, on the monodepth, the earlier monodepth papers, and Jamie on the mani-depth and some of those other papers as well. But there's, these people deserve definitely a lot of credit for a lot of the hard work that they've done on this. And there is some of the papers I flagged. And so again, if anyone is interested in how we can use depth or how we cannot use depth to do things like insert objects into virtual scenes, do consider coming along to our poster there on Wednesday where we'll talk about that. And otherwise, yeah, thanks very much for your attention. I'm happy to take any questions if there are any.
Yeah, so we should have 5 minutes or so for questions. So if anyone either in Zoom or here has questions, then yeah, feel free to come up.
Also happy to hear people disagree with me. If people think that some of those things I flagged as limitations are not limitations, definitely feel free to argue. Yeah, you had a question.
Can you go up to the microphone? Thanks. It might be worth
Oh, do you want to
moving just because there might be questions on Zoom, and I guess I don't know if, how you see the actual comments.
Hi, yeah. So I was just wondering what constitutes a well-behaved camera? Because one of the things that comes to mind, because we're assuming that we don't have calibration and such here, is that different sensor types might have things like different gamma curves. So yeah, what in your experimental work, what have you come to define as a well-defined camera?
That's a good question. I think, yeah, I don't have a principal answer to that. I think all the data sets I've seen have badly behaved cameras. Like Kitty's a good example where we have kind of vastly different appearance changes from frame to frame just because of, I guess, how the camera was set up. So I think it's good, from my perspective, I think about that question in context of like maybe the motion of the camera, which is one side of it. But then there's also like actually the appearance of the camera as well. So, we don't want obviously like pixel saturating, appearance dramatically changing from frame to frame. So those are kinds of problems we have in Kitty. And again, also with poses, we'd like to have, relatively smooth trajectories of poses. And we'd like to have scenes where we have like texture. So we don't want to be viewing just blank walls and so on. So I think those are the kinds of challenges, but I don't know if I have like a more refined answer in terms of like what are the criteria for what makes a good scene.
Yeah. Okay. So I guess as a follow-up, I mean, are there typically, would you say that these methods would work with any arbitrary cheap off-the-shelf camera, or are there certain higher quality characteristics that you would require? I mean, I know there's a lot of work with images in the wild, pulled from Wikipedia and such like, but I'm just thinking about like in a tracking or reconstruction scenario, in reality, do you need a higher quality sensor for these things to work properly?
Yeah, good question. So, back in the kind of Monodep 2 era, which is several years ago at this point, we were just taking videos from YouTube and actually training the model on those types of videos, and that works well. And others have done kind of subsequent work on that. So I think in that sense, maybe some really low quality images might have issues like rolling shutter, all those kinds of things. But actually we found that, again, with the camera being well behaved, you actually kind of don't observe as much of those artifacts, and you can actually use those types of images. Again, obviously the better quality, the better, but presumably you want it to align well with your test scenario as well.
Okay, thank you.
Yeah, you're welcome.
Checking the chat from here.
You can stop sharing, I guess.
Yeah. Okay. Yeah, if you want to read it. Oh, I guess.
Okay, so yeah, someone said, I have a question here. What is your opinion regarding absolute depth versus relative depth? Oh yeah, great question. Okay, so as everyone probably knows here, so these self-supervised methods, we're only going to get relative depth. In best case scenario, this relative depth is up to just one single unknown scaling factor. In practice, it often just isn't one. There's obviously, or there can be some kind of linear, non-linear rescaling that needs to be done. And so again, I think that there's a whole bunch of work that have figured out kind of creative ways to get around this problem. So if you know the sizes of objects that you tend to have in your scenes, you can obviously use that as a prior to kind of scale up your setting. Or again, ideally, if your method is consistently off by a single value, then it's actually pretty trivial to fix it. So I think there's some cool solutions that are out there, but it's definitely a question that gets asked all the time. When I think back to like probably 25% of the issues on the GitHub repo for Monodep 2 are how do I get metric depth from this? So yeah, people care about it.
Cool. Yeah, we probably have time for one more question. So.
Hey, great presentation. So I was wondering about depth estimation in the context of merging with other computer vision tasks. So for example, object tracking, right? If you have a set of pixels, which you kind of identify as being at a similar depth, but they're moving around in the scene, have you read about any work that integrates that with another task like object tracking, or do you think there's room for that, or are those really two separate problems that should be handled independently?
Yeah, great question. I mean, I think, there's obviously a lot of work on kind of scene flow and approaches that try to think about correspondence over time and space. I think that, like, the way I think of the question you asked is like, there's probably like two main ways. So one is like kind of these, what we'd call maybe lower level vision tasks, like correspondence task tracking and so on. But I think also depth, from my perspective, has a huge role to play in kind of semantic understanding tasks. And so clearly we've seen a whole bunch of work on trying to understand maybe the biases of the types of networks we train with respect to texture biases versus the kind of shape cues or shape biases that humans seem to have. So I personally think that there's a huge role that depth could play in helping us do better on semantic tasks, and maybe even being able to train with less images. But I think part of that is also just the limitation of the training data sets we have, that they don't align very well with the semantic task data sets that we evaluate on.
Thank you very much.
Cool. Well, we can thank Oisin again.
Thanks, everyone.
Cool. So hopefully now you can see the start for the second presentation. And yeah, so again, thanks everyone for coming. Welcome to the Monocular Depth Estimation Challenge. And so yeah, so in this talk, basically, I just wanted to give a bit of an overview of, first of all, what kind of benchmarking is, what some of the important components of a benchmark are, and then how this has kind of influenced or motivated the whole point of organizing the challenge. And then obviously I'll be covering some of the results from the participants and of course, some potentials for future work, stuff like that. So a lot of things are probably going to echo some of the things that Oisin talked about in terms of, for example, the variety of data sets, the kind of ground truths that we have, and again, how we evaluate all of these different methods. So again, the whole challenge kind of stemmed from some of the recent efforts that we've made into benchmarking monocular depth estimation. And basically, when reviewing a bunch of these papers, you find that there's quite a few common failure points. And this is kind of on both sides in terms of the benchmarks themselves that people use, but also the methodologies in the papers. So this includes things like, for example, having slightly incorrect ground truths or metrics that don't really give you much additional information. But then also in terms of methodologies of papers, there's like slight more subtle issues like performing your ablations or hyperparameter tuning on the final test set, which even though you aren't explicitly training on this data, you're still kind of incorporating it into the training loop in a kind of indirect way, which, if you keep doing it again and again, then you potentially end up overfitting. But then also this idea of like non-comparable methodologies where papers will commonly have one or two core contributions that they're proposing, but then actually when you look at the baselines they compare against or some of the additional changes that they make, these are kind of silently introduced and not really mentioned. And again, you end up with comparisons where it's kind of hard to actually tell where the improvements are coming from, if it's from the actual contributions or if it's from some of these other like silent changes that are happening in the background. So the ground truth is the starting point for any benchmark. You have a task that you're trying to perform and you need to know what the output of that task should look like. And obviously the problem is that if this is not accurate, then you aren't going to be able to get accurate evaluations out of it. So in the case of Kitty, which is one of the most widely used benchmarks, the depth comes from the LiDAR sensor. And one of the problems is that, for example, the camera and the LiDAR are never going to be perfectly aligned, which means that each sensor has slightly different viewpoints and slightly different occlusions. This means that when you combine it with the fact that LiDAR is sparse and that you also have the motion of the car that you need to account for, you end up with slight inaccuracies at object boundaries. And it might not be very obvious, but one of the things that commonly happens is that you have points from the background that bleed onto foreground objects. So for example, again, you might not be able to see it, but for example, around this area, the points in the car are mixed with points in the background, which is obviously not correct. And again, this tends to happen only, or yeah, pretty much exclusively at the boundaries of some of these objects. So instead, what we try to do is introduce this evaluation based on the SYNS dataset, which consists of aligned image and LiDAR panoramas. And one of the great things about this dataset is that it's outdoor, but it's actually dense, which is very rare again, given that it's actually collected with LiDAR. And essentially this is obtained by scanning vertically with a very high resolution and just performing a full horizontal rotation. So unfortunately, one of the things that it means is that even though the ground truth is very dense and very high quality, because each collection for both the image and the LiDAR takes a few minutes, you end up with a lot of issues with dynamic objects where you can see kind of some of these like weird spikes that happen where, you know, a car has been moving throughout the panorama. So obviously, since most of our deep learning methods can't really make use of panorama images, we generated the SYNS-Patches dataset, where we essentially sample rectangular patches from the panorama every 20 degrees, again, kind of performing a full horizontal rotation at eye level. And again, you can see how we can get incredibly detailed maps, even in these really complex scenes like trees or vegetation, where you have, again, a lot of thin structures and branches and a lot of high-level, high-frequency detail. But at the same time, it means that we also need to add this like manual filtering that helps us remove some of these artifacts and inconsistencies. And I'm guessing most of you have noticed, like, again, those weird spikes caused by the cars moving. But something that you might have not noticed is that actually none of the cars that are in the depth map actually align with the cars that are in the image. This car, for example, here on the left has vanished, just leaving its shadow. And then meanwhile, somehow this Ford in the image has managed to transform into a Jeep. And again, the reason that this happens is that because the collections take a few minutes and they are collected sequentially one after the other, you might have had dynamic objects that just so happen to be static that kind of disappear between the data collections. And so it means that when you're doing this manual filtering, you don't need to just pay attention to some of these like incredibly obvious like spiking artifacts, but you also need to actually pay attention to the content of the image and make sure that these are actually matching each other. But then one of the good things, again, about having this dense ground truth is that it means that we can generate pretty accurate boundaries for where we have boundaries between different objects and different depths, which we know is, again, something that tends to be quite challenging for existing models to predict accurately, whether it's because we have some of these thin structures or just because you have some of these like interpolation artifacts where it's hard to make a big step in the depth without just like smoothing it out. So then the other important component of the benchmark are the metrics, which is obviously the way that we actually compare the predictions that we've made to the ground truth in our data set. And again, I like to think about both the ground truth and the metrics as a kind of meta-optimization procedure, where if you have ground truth that's incorrect and metrics that are either incorrect or don't really give you much information, then you might end up drawing incorrect conclusions from your research and your contributions. And that means that it will kind of guide the research in a wrong direction, where actually your contributions might be trying to either game the system in terms of the errors that are in the ground truth, or just trying to deal with some of these errors rather than actually improving the method. And again, kind of going back to Kitty, one of the things that we find is that some of the metrics that are commonly used are either just incorrectly computed or saturated, or again, don't really give you much additional information about how the models are failing. So for example, so again, since it was introduced, this square relative error has basically been missing a square in the denominator. But again, even though people have noticed, they just carry on using the same metrics because that's what previous papers used. And again, for example, when you go into some of the other metrics that people commonly report, like these accuracy metrics, when you use some of these more lenient thresholds, you end up with 7 or 8 out of 10 methods with exactly the same value. So there's no real point in reporting this metric because it doesn't actually tell you anything useful. So what we do in this benchmark is we try to favor some of these metrics that are a bit more interpretable. So things like mean absolute error, which is simply measured in meters, or the relative error, which obviously is measured as a percentage error. But one of the other things that's a bit of a problem is that the metrics that I was talking about so far and that people commonly use focus only really on evaluating the accuracy of the depth along each ray, where they're comparing one point in the ground truth to one point in the prediction. But actually, the real objective of depth estimation is to try and recover the 3D structure of that scene. So this paper by Ornick et al. Proposed that instead of using these kind of like what we call image-based metrics, we should actually use point cloud-based reconstruction metrics. So for example, they proposed using things like F-score or intersection of a union based on the precision and recall, where you assume that if a point is within 10 centimeters of the ground truth, it has been correctly reconstructed. And again, one of the things that they find is that, for example, if you use some pretty like standard baselines, like so for example, Oracle NN is simply retrieving the closest image in the training data set to the test image, or if you use simply like a median plane where the whole scene just has a single value, then actually these simple baselines actually can perform better than our trained models. But again, when you actually try and incorporate something like the structure of the scene and these more 3D metrics, then we start to see how the actual models are actually performing a bit better. And then again, since we have these ground truth boundaries for the objects, then we can introduce some of these metrics proposed by the IVIMS benchmark, where essentially you're looking at the chamfer distance between the predicted and the ground truth boundaries in either direction. Cool, and so now we can get on to the actual monocular depth estimation challenge, where again, kind of as a whole summary, this is based on the SYNS-Patches data set. We're trying to incorporate some of these more informative or just different style of metrics. And then we're also providing the participants with a set of updated state-of-the-art implementations for existing algorithms, and obviously creating this centralized evaluation where we can make sure that everyone is following exactly the same procedure, evaluating the same images, and again, just trying to make sure that everything is quite consistent. So here you can see some of the examples from the SYNS-Patches dataset. And again, one of the really good things about it is that, again, it just has quite a nice variety of scenes where you can see, for example, slightly more traditional urban and industrial scenes, but then we also have some like agricultural or farms, and then natural scenes like the forest, but again, then combined with some indoor scenes like cafeterias or lecture theaters. And yeah, so as part of the challenge, we provided the participants with an updated dev kit that has these 16 state-of-the-art algorithms, but that have all been improved using some of these common design decisions. And for example, what I mean by that is that one of the things that we found is that actually in a lot of cases, simply modernizing the choice of backbone and using a newer, better backbone gives you significantly better improvements than introducing some of these more complex contributions, which require you to calculate additional losses, predictions for multiple frames. And again, yeah, simply just replacing the backbone, which is something that nowadays is very easy to do using libraries like TIM, can be a much easier way of getting these improvements. So as the baseline for the challenge, we use, again, this updated implementation for the GARG method, which I believe Oshin mentioned. But again, we modernized it by replacing the ResNet backbone with CompNex instead, and using the traditional like DispNet decoder. And as a reminder, the GARG method uses only the stereo frames in order to compute the photometric losses, and it just uses the base photometric loss without contributions like monodepth 2, where you have the minimum reconstruction or the auto masking and things like that. And so, yeah, so now we can actually get onto the results of the challenge and some of the submissions that we received. So unlike the previous edition, where we only accepted submissions from self-supervised methods, we decided to open up this edition to supervised methods as well, with the idea that this, helps you get a better overview of the field as a whole, but then also it helps us to see what the kind of gap between these different forms of supervision is. Which obviously is one of the things that Oshin was talking about in terms of there's still probably a pretty big gap. So yeah, I'll try and give a brief summary of each of the submissions. Obviously, this is going to be quite surface level, so if you're interested, I do recommend checking out the paper. But basically, we received 4 supervised submissions and 4 self-supervised ones. So the first one was Team DGI ZJU, where their network was composed of a CompNex backbone and LERES decoder. And again, since it's supervised, they trained it on quite a large collection of 10 or 12 different data sets, which includes a mix of indoor and outdoor data. Team Pokemon similarly used SWIN v2 architecture, which is obviously a transformer-based one, combined with the new CRF decoder. And again, since it was supervised, they trained on this larger collection of varied data. But they additionally introduced this multi-stage refinement where the network first makes a low resolution prediction, which is refined by a second network into a higher resolution prediction. Team CV Challenge was based their method around Zoe depth, which is actually an extension to things like Midas and DPT, which again, one of the most popular and kind of well-known supervised methods at the moment. And then what they did is, since these methods tend to just give you relative depth, they fine-tuned it on either Kitty or NYUD, and then applied each model depending on the type of scene that we're evaluating. And again, in this case, they introduced the multi-scale refinement, which is based on boosting mono depth from CVPR a couple of years ago, I think now. And then the final supervised method is based on Bixel Former, which is a transformer-based architecture. And in this case, they only trained it with Kitty, but they included additional contributions like this cut depth augmentation. In terms of self-supervised, we have Team IMEC ID Lab from the University of Antwerp, which used Convex v2 combined with HR depth, which is a high resolution decoder, but they modified the decoder to use deformable convolutions rather than just the vanilla convolutions. Similarly, Team GMD used Convex extra large with HR depth, but again, in this case, it was just trained on Kitty. And a recurring team from last year. So we have Monovid team, which obviously is based on the Monovid architecture that they proposed. But they were the only ones that actually also introduced this supervision using proxy depth. So again, not necessarily ground truth, but simply commonly either obtained by handcrafted disparity or from another method. And in this case, they obtained it by pre-training a RAF stereo network on a trinocular data set, again, in a self-supervised manner, so it's still not actually using ground truth annotations in order to train. And then the final team was USTC IAT United, where their submissions were based on essentially a weighted combination from the predictions of different models, in this case, DiffNet, feed depth, and monodevsnet. So here I'm showing the results on the SYNS-Patches benchmark, where again, so these orange methods are the ones that are supervised and actually use ground truth depths for training, and all the blue ones are the self-supervised ones that just use the photometric consistency across frames. And you can see that when we rank the submissions in terms of F-score performance, the baseline kind of ends up halfway through the pack. But actually, one of the things that we find is that a lot of these methods, especially some of the self-supervised ones, even if they don't outperform the baseline in terms of F-score, they tend to be better at some of these image-based scores like mean absolute error or absolute or relative error. But actually, we see quite a significant improvement in performance from the previous edition, where the top supervised submission improved the F-score by about 27%, whereas the self-supervised one improves it by 16, almost 17%. And again, we see similar improvements in terms of the relative and image-based metrics. We can show some of the predictions from the different models. So again, it might be a bit hard to see, but you can see again that there's this very nice distribution of image types and kind of like scenes that we can represent with the data set. And to just go into detail with some of the using some of the submissions. So you can see that, for example, when you go to some of these agricultural scenes, and again, what Oshin was saying in terms of thin structures, we obviously see that the supervised methods are a lot better at that than the self-supervised ones. But then also one of the other quite common problems that self-supervised methods have is that you have, again, it's quite hard to see from these from this distance, but there tends to be these like texture copying artifacts where, for example, if you have a brick wall which has, you know, the brick and the cement in between, supervised methods are quite good at dealing with that. But since self-supervised ones rely on the photometric loss, they also tend to copy some of these textures where there's not a change in depth, but the fact that there's texture in the image makes the model think that there is a slight variation. And then obviously, since all of the self-supervised methods are still currently only trained on Kitty, they tend to struggle to generalize the scenes beyond the automotive data sets. So again, as soon as you take them outdoors to more natural scenes where you just have trees and branches, they tend to fail a bit more spectacularly. And then when you go indoors, you also see some of these weird cases where, for example, they still tend to predict geometry that's kind of similar to an outdoor scene, where it's kind of predicted this as like ground plane that kind of keeps extending, whereas obviously we know that the room, there should be a massive plane right there, which again, all of these supervised methods tend to handle a lot better, mainly just because they actually are able to train using this type of data. So that's pretty much it in terms of the challenge. Some of the main conclusions that, again, we draw is that obviously there is still a pretty significant gap between supervised and self-supervised models. And one of the main reasons we believe this is the case is, again, the fact that supervised models, ironically, are able to actually train with a much higher data diversity, relying on, outdoors, indoors, and different types of scenes within that. Whereas all of the self-supervised models still rely exclusively on automotive data. Again, one of the things that we actually find is that some of these self-supervised methods especially still find that updating the backbone architecture and upgrading it to larger or complex V2, for example, is still one of the most reliable ways of actually improving the performance. And then one final thing that I wanted to announce is that we are looking for collaborators that might be interested in helping us organize future editions. So yeah, if you might be interested in something like that, then please do get in touch. And then actually I have one final thing, which is a bit of a sneak peek into some of the work that we've actually been doing. Unfortunately, I can't discuss in too much detail because this is work that's currently under review, but we're hoping that we'll be able to share it pretty soon. Where again, we were trying to deal with some of these problems that we've been talking about in terms of the data diversity and the generalization capability of these models, where actually we are still, by collecting data from YouTube or some of these online sources, we're able to collect a much more varied training data set. And again, since these methods are self-supervised, then we don't actually need to obtain any ground truth or even any camera calibrations. And you can see that, for example, the same model is able to generalize pretty well across different natural scenes. So, for example, we have these like foresty scenes, or even like forest with a lot of snow where you don't have much texture, but then also even like more desert and sandy scenes. But exactly the same model, without changing anything, is also able to actually adapt to some of these indoor scenes with humans and some of these very different structures than what you would see in outdoors. And again, what we actually find in this case is that we are able to match, or even in some cases slightly outperform some supervised models. So yeah, hoping that we'll be able to share more information very soon. But yeah, keep in touch to hear more about this. And then yeah, that's pretty much it. So if anyone has any questions, we'll also have a few minutes for that. So yeah, thank you.
Thanks for that talk, Jamie. Yeah, I actually have a couple of questions, but I'll just ask one, and if there's time, I'll ask the second one. So the first question is kind of a technical question about the use of a 3D metric versus a point cloud metric versus array metric.
Yeah.
So it seems like there's two things going on there. So one is that you're now measuring distances in 3D space as opposed to just along the array.
Yeah.
But the second is that you've also changed the error measure from a distance measure to a classification measure, right? By doing F-score and IOU, right?
Yeah.
So my question is, what's the relative importance of those two things? So for example, could we still maintain a distance measure, but measure distance in 3D? And would that, how much of the problems that have been identified previously would that address? Or is it for some reason critical to turn it into a classification?
Right. Yeah, that's something that we haven't really looked into too much, because again, we essentially use the metrics that someone else proposed and that they kind of spent some time looking into. Yeah, I'm not sure. And one of the things is obviously with these F-score metrics, because you are looking at the, I guess, like classification, you need to decide what the boundary is between a point that's correct or not. So that's something that we played with a little bit, but again, it makes it quite hard because there's no good way of like dynamically setting some of these things, because you have obviously like indoor scenes where because the general depths are much lower, then you tend to have much higher F-scores just because of the nature that, all the points are closer. So yeah, that's a good question. I'm not sure how you would separate those two components. Because one of the other things that the F-score changes is the fact that, again, because we aren't looking at the distance comparing the same point in the ground truth with the same point from the prediction, it's hard to figure out what metrics you would use otherwise in that scenario. Because again, if you're just comparing those 2 points in 3D, then it's still like comparing the depth along that ray.
Well, I mean, can't you just measure the depth in any direction? So just
Oh,
choosing
right,
what's like
yeah.
iterated closest point, just the closest. point,
Yeah.
Yeah.
Yeah. Actually, yeah, I guess that would be I think that was one of the metrics that they also proposed in the benchmark. We just didn't report it. But yeah, it would be interesting to like look at those other metrics as well.
I have another, do I have time for another
Yeah.
question? Okay. So this one doesn't really have an answer, but you gave us a sneak peek at a new unsupervised method.
Yeah.
That by training on a bigger diversity of types of scenes and motions might do better.
Yeah.
In general on a data set like SYNS. So you also talked about a different supervised approach, which is essentially model selection, right? So you try to figure out what kind of scene you're looking at, and then you switch models. And so I guess I want to ask, is there sort of two parallel strategies here? Sort of the data strategy versus kind of a semantic strategy, because you could further elaborate that semantic strategy to say, well, it's an indoor scene, and I think it's a scene of like a kitchen or something like that. And if you have any general comment about the relative merits, that's
yeah. In this case, we focused on the data diversity side of things because, again, we feel like it's something that people haven't really looked at in terms of self-supervised learning, where again, people have kind of been stuck on evaluating on Kitty and just, measuring progress based on that. So in that sense, that felt like the big challenge that we wanted to actually solve. One of the interesting things is that, and part of it is that we also wanted to use as little annotation as possible, where you have, you don't need to generate any reconstructions, you don't need to calibrate the cameras, you can just train the model and just like, with the idea that you could potentially keep on scaling the data set with new videos as you go along. But yeah, there definitely has been some interesting work recently in terms of that, like training multiple models. And this has mainly been the case with supervised methods, where again, you have this very different distribution in metric depth between indoor and outdoor scenes. So yeah, that's something, and again, there's different ways of doing it, but it's not something that I've really looked into. Yeah.
Hi. Yeah, very interesting challenge. A lot of the self-supervised depth methods, or almost all of them, basically rely on, I guess, a reconstruction loss, which is based on photometric consistency. But I guess in many ways, photometric consistency is very, very limited. I mean, you have dynamic objects, you have, I don't know, translucent surfaces, or all sorts of different effects. Did you see any interesting work regarding self-supervised depth estimation methods that rely on other sorts of self-supervision other than like reconstruction losses?
There aren't that many, to be honest. One of the things that some people have tried is still using these reconstruction losses, but instead of using the plain RGB pixels of the image, you can use feature descriptors, which theoretically should be trained to be more invariant to like lighting and viewpoint conditions. So you'd hope that they're more robust. And again, for example, if you have something like nighttime data, again, the photometric error there goes pretty crazy. So sometimes using these more robust representations like descriptors can be helpful in that sense. The other main form is that trying to introduce like pseudo labels, where you might use handcrafted disparity to try and estimate a proxy depth, which isn't going to be perfect, but it gives you, when you combine it with the photometric loss, it can help to make those models also a bit more robust to things like dynamic objects.
Yeah, and maybe a follow-up question on that. So do you think self-supervised like depth estimation especially sort of in a general context as you showed it for arbitrary videos, maybe make sense without considering dynamic objects in the reconstruction?
Yeah, so that's also obviously one of the things that people have tried to focus on a lot. And I do think some of the contributions like Monodep 2, which Shoshin was talking about, do help a lot with those things where, for example, if you're dealing with occlusions, then that also kind of implicitly helps to deal with some of these motion things. But there's also a lot of work that has gone into, for example, using a combination of like motion masks and semantic segmentation, where you can essentially try and predict an additional motion for each dynamic object in the scene and use that to account for the incorrect correspondences. Or if you also use things like optical float, that might also be a way of, getting the actual exact correspondences and trying to do some more advanced like masking or filtering with that.
All right,
Yeah.
thank you.
Cool, thank you. Great, so I think it's now time for the challenge participants. So the first presentation will be by Lynn. So if you're there, then yeah, please unmute and share your screen.
Hi, Jamie. Can you hear me?
Yeah.
Okay, let me show my screen. Can you see my screen?
Yeah.
Okay, nice. So let me start. Then I'm Lee. So I would like to present our methods improving self-supervised learning for the automation to deformable components. Our team, Professor Cipress, Dr. Ali and me from ID Lab, IMS and University of Antwerp. So yeah, our goal is to evaluate the model on the challenging sympathy to the set. And we certainly face some constraints that cannot train on any sample of sympathy to the set. And during that inference time, we can use only single image for inference. So our approach is to use monocular optimization based on the self-supervised learning on the well-known PT data set. And our methods will consist two steps. One first step, we establish baseline model based on self-supervised learning. And for the second step, we improve the baseline model to several observations. So here's some example from sympathy data set. As you can see, unlike with Kitty dataset, this dataset consists diverse nature scene, not only on two scenes, but also on inside building, room, the fields, the fish, and river, garden, many others all. So such make it a challenge. So we based on the model proposed by Goda, which the model consists of three methods. The depth encoder, we transfer picture from drawing images, and depth encoder and the depth decoder is predict the depth map from picture, and the PONF just like the gratitude for training. So this model is then to pre-construct the graphic image from the depth and transformation matrix, and then is to compare with the drawing image to conduct photometric loss for training. So for training loss consists of two main components: the automatic photometric loss and smoothness loss. And during using multiple scale for training, multiple scale network, we erase the loss of the overall number of scale. And to optimize the model for this one, we search the network to multiple network architecture components. We search from BREDNet family, from BREDNet 40G to BREDNet 101. And for the decoder, we search from the background precision model on the ImageNet 22K from BREDNet 18 to combination between hues. And for depth decoder, we succeed on monocular depth tool, DDB depth, and channel attention depth, resource depth, and deepness. And for experiment, we run our experiment on with image size of 192 and 640, and we choose by size of 4, and smoothness loss factor is 0.001, we turn over 30 epoch. And we use 50 Asian Zoom split. We consider more than 40 training monocular chiplets, which the statistics frame are removed for training. And we train our experiment on I100 server. So we found out PowerNet with VNet 18 and depth encoder question on internet with the architecture convergence between here and high resource and depth bring the best performance, and we shift 14 and 14.9793 advanced score on SYNS-Patches validation test. So for this tool, we have some observations that unlike the KT, the SYNS-Patches that consists more diverse natural scene. And the challenge was how to balance between the encoder pre-train and training with KT dataset, but achieving good performance on SYNS-Patches dataset. So another observation that training with more ample and diversity dataset bring more benefits. So we aim to use Monocular TT is a standard split for training of finalized model. So here we propose 3 main improvements to improve our model. The first one, we propose a training strategy for encoder. Thus, we train the pre-trained encoder a few epochs and freeze it and continue training the model. And the second one, we improve the decoder architecture. Thus, we use a deformable component to replace the convolutional network 2D to improve the decoder performance. And the last one, we train the finalized model on the TT using benchmark split. We consist near 72 images, that more than 50 is in two split. And for here is the detail of second improvement. Thus, as you can see, already know high resource and depth that consists feature instruction at the I scale and the feature fusion and despite the decoder that rely on the convolution 2D iconosite 3x3, and I modified Harrison depth decoder with deformable coordinates. We apply it in 3 blocks, feature extraction at the I scale, feature fusion, and depth decoder with the deformable components. And here is the result we achieved on SYNS-Patches validation set with improvement by training strategy. We improved from the light to 0.22 of advanced score, and by adding the improve on decoder, we improve it to 0.13 of advanced score, and finally we train the model on 50 Asian benchmark split. The model improved near the 0.44 advanced score. And finally, our result on the target SYNS-Patches dataset what here in little box. So there are some examples that we randomly sampling from SYNS-Patches validation set, and the qualitative so the improvement to adding improvement from the baseline model. Thus, we saw the significant improvement from baseline model. So we also provide we evaluate the final line model of the Kitty is in benchmark to compare with other state method, which dataset consists of 652 samples, and our method with here we baseball shows we kept improve from figures just coder. So in conclusion, we improve multiple high resolution depth with deformable components, and we propose a training strategy with the frozen depth coder of the training to evolve on Kitty to improve the adaptation to the SYNS-Patches dataset. And the evaluation result on SYNS-Patches and Kitty is in split. So our model achieves the stage of performance. And for future work, we will improve the depth encoder to reduce the theory background and also reduce the computational cost. And also we improve the depth encoder for many other benefits and also explore the domain adaptation. So I would like to thank to our IG lab at MH and our university as well, and the excellent people, monocular depth benchmark provided by Jamie. And there are some main reference from our method. So thank you very much. If you have any questions, please go to discuss. Hello?
Jamie, we can't hear you.
Sorry, I forgot to unmute myself because I muted myself while the presentation was happening. Yeah, I was asking, saying there's time for one question. If there's anyone on Zoom that has a question, and if not, we can move on to the next presenter. Yeah, I can't seem to see anything. So yeah, again, thanks a lot. Yeah, I didn't hear it before, but yeah, thanks a lot for that presentation. So yeah, so the next presenter is Wei Yin, who is the winner or is part of the team that won the supervised track of the challenge. So yeah, if you can
Thank you very much.
And share your screen.
Okay, I will share my screen. Can you see it?
Yeah, we can see it.
Yeah, okay, I will start. So here our work mainly do the actually mainly want to do the robust metric estimation and then to participate in this challenge. And yeah, maybe I will spend some time to review the previous method. I distinguish them to the learning metric depths or absolute depths and relative depths. So learning metric depths will previous method mainly assume all data are captured by the same RGB cameras sensors. So they will train the model on that and enforce a regression or classification laws on that, and then the model can predict accurate metric depths on that. And so many methods have been proposed, and they focus on constructing more robust features and geometric features and anything for accurate metric depth. And they have achieved higher accuracy on metric benchmarks such as NYU or KT. But the problem is that if the model is trained on NYU or KT or any metric depth dataset on a single dataset, they have a very low generalization ability over diverse things and various cameras. And even though maybe they can work on some similar things, but maybe because of the cameras are different, so the metric is not that accurate. Also, there are some methods trying to solve the scene generalization issues. Many methods propose to learn the relative depth or affine invariant depth. So the relative depth, they will mainly represent the depths, in a ranking way. I mean, it means one point farther or closer than large one, and the affine invariant depth means that the predict depth is up to an unknown scale and shift. So such as methods such as meters, layers, DPT, DW, red web, anyway, they will use large scale data sets in training, and they will enforce the ranking nodes or scale shifter invariant nodes in training. And yeah, they can achieve very strong generalization over diverse things, but the problem is that the predict depth is relative or affine invariant. So they cannot achieve any scale, or it's very hard for them to recover the shape. If they even the affine invariant depth, if they want to recover the accurate shape, they have to use a ground truth steps or any metric information for the recovery. For example, such as the layers in the red part, and it can do high quality shape recovery. Yeah. So, but in this challenge, we can say that they have two requirements. The first one is these required methods should have strong generalization, and so the test will be in the weird things, indoor, outdoor, and anyway. And also the depth should recover high quality 3D shape. So we think the existing method maybe can not work well. I say the metric depth, they have to train on specific camera captured data set, so they have no generalization quality ability. And for the relative depth, they cannot achieve high quality shape. So the F score will be very, very low. Yeah, all right. So for our method, first we have to conduct large scale data set. This is very important to ensure the generalization. All right. So we conduct over 9 million diverse data. There are many, most of them are from the autonomous driving data sets, such as DDAD, Waymo, Lyft, Agaverse, Drive and others. Also some outdoor data sets such as DML and Mapillary, and also some indoor data sets such as task colony. And also actually the data set quality varies. The indoor and the autonomous driving data set are captured with a LiDAR. So they are in very, very high quality, but some indoor data sets are captured, outdoor data sets are captured with stereo cameras. So, and we have to use a stereo match method to obtain the ground truth. And also such as a Mapillary, as the data set actually is constructed with struct from motion and multiple stereo. So the quality actually is not that good. So if we merge them for training, and if we directly enforce the regression nodes, it will be an issue. The metric ambiguity. So I show a case here. For example, for DDAD, there are the DDAD data set is captured by the ring cameras, but actually the ring cameras have different focal lengths and different the image have different appearance. So you can say for the left camera, actually the the car in the right bounding box, actually it is in the same distance. But for the left camera, it is much smaller. But for the front camera, it is much larger. All right. So this will cause ambiguity if we don't tell the model that the images are captured with different cameras. So it will cause ambiguity because they have different size on the image, but you tell the model that the distance are the same. So the model will fail in this training. So how to solve it? Actually, it's very easy in our training, and we propose a canonical space transformation. We're trying to transform all different kinds of metric depth data into the same space. The idea is what it aims to trying to tell the model that the currently the training data are captured by the same camera. All right. So we just want to do this. So do this transformation is very easy. And we propose a canonical camera, and it has a canonical focal length. And for each data from our training data, we have their ground truth focal length. All right, we will know the scale between the data size focal length and the canonical focal length. Then we get the scale, and then we will scale the ground truth steps. And during training, we will transform the ground truth steps to the canonical space, and then we can merge a large scale data size in training. And during this training, actually, the model can learn the metric depth. The absolute depth actually. And but also the problem, the requirement is that in the inference. So if you want to get the metric depth, you should tell the model the focal length, because the predict depth is in the canonical space. If you want to get a metric depth, you have to transform the back to the original space. All right. So, and other training details such as the model, we use complex large backbones, and we use our previous work, the Laros decoders, and our model, learns the metric depth, absolute depth, and the depth range is in 0.3 to 150 meters, and the training size is 512 by over 900. Yeah. So after this training and from the paper, we can achieve the rank the first in almost, I say, the almost all the things, indoor, outdoor, and urban. Anyway, nature. But we also found that our model have some problem. We found that the edge is not that accurate. Maybe, this is maybe because our training data is most of data is very sparse, because you know the LiDAR capture depth is very sparse. It don't have enough edge information. So I think this is a problem that we model cannot work well on the accuracy, and with I missed the supervision. Sorry. We use 4 supervisions: L1 norms and the virtual norm norms, the pairwise normal regression norms, and a random proposal normalization norms. Yeah, the norms is very easy, and they have been proposed by previous works, and we don't put many tricks on during the training, just merge them together for training and use a very simple encoder decoder. Yeah. Actually, maybe more result. Apart from that, we want to show here on Katie. Actually, as the Katie is not enclosed in our training, so actually the Katie is also a zero-shot testing, and actually we combine our model with the joint SLAM, and we found that our model can do the metric SLAM. I mean, reconstruct the point cloud actually have the metric shape. We can measure the size of the cars and from the reconstruct point cloud, and also we found that trajectory is much more accurate than the joint slant. Yeah, it seems it can alleviate the scale drift problem. Yeah, that's all. Thank you.
Yeah, thanks for that presentation. Again, we probably have a few minutes if anyone has any questions in person or on Zoom. So yeah, let us know. Yeah, we have one question in person, so hopefully you should be able to hear them. Yeah.
Okay,
yeah, maybe. Yeah.
Yeah. Okay, thanks. I really enjoyed that talk. Couple of questions. So you're correcting for focal length between the ground truth data sets, which is a really nice idea. I'm wondering if you considered, so are all your data sets using a horizontal camera? And so have you considered correcting for differences in height and in general, you know, tilt and roll if you wanted to extend to cameras that weren't horizontal and weren't, you know, were rolled?
Sorry, I don't get the.
Well, maybe I didn't understand, but just looking at your equation here, are you just correcting for principal point and focal length, as far as I understand? Is that correct?
Okay, sorry. Maybe let me explain this in detail. Spend a little more time. Sorry. Actually, during the training, you know, all the training data have the focal length, all right, because I used a very high quality training data, such as DDAD Waymo anyway, and they provide the calibrated the focal length. So during the training, we will set up a canonical focal length. For example, the focal length is 1000, all right? So during, as I have explained, if the focal length is different, the captured object scale, it will be different. This will cause metric ambiguity. This is the main problem if we merge them together and use L1 loss for training. The main problem in this. So
right. Yeah, that was clear. I was just wondering if there's differences in the other camera parameters, the extrinsics, if you correct for that as well.
Yeah. Of course, such as center point will also be adjusted. Yeah.
Okay, so you're adjusting both the intrinsics and the extrinsics into your canonical
camera. Yeah.
Okay. Second related question is then if you're mixing long focal length and short focal length, then for the long focal length images, you'll be missing a lot of information in the outer region of the images. And so for training, does that pose any problems?
Yeah, this is a very good question. Actually, for this method, it has limitations on this part. We found that when we testing, if we test on very long focal length, for example, maybe the focal length is 10,000, we found that the metric recovery will be not that accurate. We found that it can work. Seems that it can work on focal length distributing. For example, focal length will be just in the range about 300 to 400 to the 2000. It seems in this range it can work much better. But if out of this range, you mean the very long range or very short, very small focal length, it cannot work very well because in this way it will have a very special, I mean, the visual effect, you know, such like the moving, in very many moving industry, they will use a very long range, large focal length to get some visual effect, and it seems that this model cannot work on this kind of images. But maybe we will work later and try to fix these bugs maybe in the future. Yeah.
Okay, thank you.
Cool. Yeah, I can't see any other questions on Zoom. So yeah, thanks a lot again.
Thank you.
And yeah, so that basically concludes the first half of the workshop. So we're going to be taking a bit of a break now. So we'll be back at 20 to 11, where we'll be having the two keynotes by Daniel Kremers and by Alex Kendall. So yeah, I believe there should be a break going on somewhere outside, and hopefully, yeah, we'll see you in a bit. Thanks.
Yeah, I haven't really had time to look at the schedule, so that's going to be. Oh yeah, yeah.
Hi everyone. Should I mute? Can you hear me?
Yeah. So if I speak from this one, yeah. Works.
Cool. Hopefully you can hear me all right from Zoom again. But yeah, welcome to the second half of the workshop. So yeah, we have 2 keynotes left by Daniel Kremers and Alex Kendall. Yeah, so the next one is here by Daniel. So Daniel Kremers holds the chair of computer vision and artificial intelligence at TU Munich. He has co-authored over 500 publications in computer vision, machine learning, robotics, and applied mathematics, many of which received awards. He was listed amongst Germany's top 40 researchers below 40. He received the Gottfried Wilhelm Leibniz Award in 2016, the biggest award in German academia. And he's a member of the Bavarian Academy of Sciences and Humanities. He is initiator and co-director of the Munich Data Science Institute and Munich Center for Machine Learning and LS Munich. He has served as founder, advisor, and investor to numerous startups. So yeah, you can welcome the presenter.
Thank you, Jamie. It's a pleasure to be here. Thank you for having me. And thanks everyone for coming to attend the session. So this is work. Sorry, you cannot read all of it, but let me read it for you. So this is work that I'm presenting that's been done by a lot of my current and former students, in particular, Felix Wimbauer, Lukas Köstler. Felix is here. If you have questions about technical details, here's the person to talk to. Lukas Köstler, Nan Yang, Lukas von Stumberg, Jacob Engel, and as an external collaborator from Oxford, Christian Ruprecht. It's about monocular depth estimation, but going from monocular depth estimation to full-blown 3D scene reconstruction. So let's go into details. There's 4 parts here. I'll first start with more classical approaches to structure and motion, or SLAM, visual SLAM, and in particular direct visual SLAM. Then I'll come into how we got into monocular depth estimation, and that is through SLAM. Our aim was not to do depth estimation really, but to improve SLAM algorithms. And the question was, how can we leverage the power of deep networks to do that? And this is how we stumbled into this field of monocular depth estimation. And then we went further and looked into monocular dense reconstruction, and in particular into getting kind of full-blown 3D reconstruction from monocular, say, self-driving videos. But let's go really back in time to the origins of computer vision. This is one of the pioneers in this field. Many of you will not have seen this picture because it's very hard to find images. You know, people who didn't have a Facebook page at the time. And this is the only picture I could find. It's actually a drawing that he made himself, kind of Erwin Krupper. And one of the things he proved, and people in his time were able to show, is that if we get 2 images of a 3D scene, it's a very classical result, and we find 5 corresponding points in the 2 images, then we can recover the relative camera motion and the 3D structure of these points.
So you're sharing the screen. Can you change your screen resolution to
Sorry.
1920 by 1080 so people can see your slides?
Okay, that's a good point. Thank you. How do I do that again? Anzeigen, Einstellungen.
Don't mean to interrupt. Your slides.
Yeah, I noticed that. Isn't there something with the resolution?
Check on the, click on the second screen. I believe it's this, the second screen. Screen settings.
Yeah, sorry, we should have checked that. I saw it earlier, but I pointed it out, but then there was.
I can't help you with
the German, right?
Yeah, sorry.
And
should be screen resolution in
I haven't had this issue for a while, so I don't actually. Does anyone remember? You should be.
where it is in 11.
Oh, here.
Oh, there you go.
1920
by 1080.
Let's see if that does the trick.
And it's still not there. It went back as soon as you, I think you have to change screen number 2 to 1920.
Okay.
Screen number
Screen
two.
number 2, and then
Yeah,
that's
it's
what it
1200.
is.
It's set to 1920 by
Wow.
1200. 1920, 1080. Sorry to interrupt you. Now, back. No, it keeps going back to that.
No, but it's
Well,
better now. So
It's,
at least
no,
the
it's better.
bottom part-
It's better.
Yeah. Sorry about the complications. Let me see if the Zoom is still running. Does the Zoom audience have the right screen? Okay, good.
Yes.
All right, sorry for the complications. Now you see a little bit more of what I was going to tell you. So Krupa, the classical result of Krupa, and based on this result, there's a lot of kind of 3D computer vision that emerged in the 70s, 80s, and around the 2000s, we saw some of the first real-time capable, what was then called structure from motion algorithms now.
Yeah, sorry again.
Sorry, share screen. Sorry, let me restart. And now, Zoom. No Zoom. No. Okay, is that better? I think now it's perfect. All right, so a lot of real-time capable visual SLAM algorithms emerged. Structure for motion, it was called. Now it's often called visual simultaneous localization and mapping. And many of these approaches, and this is just a few example works in this area, some of the most seminal works in this field. Many of these actually follow very closely in Krupa's footsteps. They start by taking 2 images. They start by sampling points from these images, putting points in correspondence. And once you have points, you can basically start reasoning about camera motion and 3D structure. What we've been advocating for the last a little more than a decade now is so-called direct SLAM approaches, which do not do this intermediate abstraction step. So they don't start with extracting points. They don't start by putting points in correspondence, but they try to go directly from the brightness images of your sensor to a reasoning about 3D structure and camera motion. And there are many reasons why you would do that. First of all, from an engineering perspective, any mistake you make in point correspondence estimation will propagate into your results and deteriorate performance on a level that you can typically no longer recover from. But secondly, if you look at it from a statistical data analysis point of view, you always want to be as close as possible to your raw sensory data, and that is the brightness values. And so the key difference between the direct and the classical key point methods is that in the direct methods, what you're minimizing is a photo consistency loss. So you're saying find a camera motion and a 3D structure such that if I project these colors into the world and back out into the other camera, the colors should coincide. And this color consistency drives all the estimations of 3D structure and camera motion. And one of the first approaches that we published in this field was a technique called LSD SLAM for large-scale direct monocular SLAM. Pity that the top is cut off, so you don't see the title, but believe me, it's called LSD SLAM. And here you see it in action. It's a system that can capture the real world in real time at a fairly large scale. That's why we call it large scale. It was at the time, to my knowledge, the first real-time capable system that could really map environments at a large scale from just one moving camera. We went further, and so and you have to understand the issue with LSD SLAM is that we basically did an alternation of camera motion estimation and 3D structure. This is then the follow-up work called direct sparse odometry, where we actually jointly estimate camera motion and 3D structure. Much like Krupa suggested, to estimate that this is a chicken and egg problem, here we do it jointly, typically over a time window of k consecutive frames. This can be optimized in real time. And obviously, if you track a camera, just a single camera over thousands of frames, you will make errors, and that aggregate into what's called a drift. And so you see that drift here, the bicycle on the top left is actually reconstructed twice. So there is a drift, but the drift is fairly small. If you want to get the drift smaller, and this has been our endeavor for many years, there are many ways to go. The first thing is, and this is what you would do in any robotics context, is you would tap into additional and complementary sensors. That could be a second camera, could be GPS, or it could be inertial. So here's one example. This is enhancing direct sparse odometry with an inertial. It's a technique that Lukas von Stumberg called DMVIO, for delayed marginalization. I don't want to go too much into the technicalities, but here you see the system in action. It uses basically what you have on a smartphone, a camera and an inertial sensor. But it can track the system at very high precision. And here we go up to the third floor and into a slide that's a dark tube. It's completely dark halfway down the tube, right? You don't see anything. And still the system can track the camera-based camera inertial system at very high precision, as you see here. Where we can go up to the second floor again in our building. And now we know why there is a slide going 3 floors down. It's for us to quantitatively evaluate performance of SLAM systems. And you see there is a drift, the walls are, there's a slight offset here, but it's quite small. And so this is extremely robust, and this works indoor and outdoor. I don't, for time reasons, I'm not showing this, but there's also videos of this running in a car, right? And it's very lightweight because it's just a single camera and an inertial sensor. So it's small and it's dirt cheap. And it can track at very high precision and very high robustness. And it generalizes well because it's not learning-based. But now I come to learning-based approaches. The first thing you can do, and this is the things we developed at the startup Artisans that we created, we developed sensory systems, but then also algorithms to create semantic 3D maps where we can distinguish drivable area, sidewalks, cars, pedestrians, you name it, at very large scale. And this is basically 8,000 kilometers of mapping that we generated in just a few days, by putting our sensors into a whole fleet of cars and just running these algorithms and merging things in the cloud. And I think this kind of semantic 3D maps can be quite useful for self-driving cars. They tell you what the world is like in 3D, right? And where there are obstacles, and it tells you what things you're looking at. Is it, and that's sometimes important to know, is this a trash can in my driving corridor, or is it a child? Makes a big difference for autonomous driving. And the important thing is the world we live in changes very quickly, right? This offers you the capability to do large-scale semantic mapping at very low cost. You just tap into cameras, basically. And these are nowadays omnipresent. And so with these techniques, we're increasingly trying to establish the camera as the lead sensor for autonomous driving. Now, how can we leverage the power of deep networks to improve SLAM? And this is an important endeavor here. If you look at deep networks, initially they were for object recognition, image classification, but then this is work that we did, for example, in 2015, we showed that you can also do other low-level vision with deep networks. We showed in this flow network that you can do optical flow estimation with suitably trained networks. And that kind of opens the way to look into what other things can we do with deep networks. Here's another work, also 2015 from Cambridge, from Roberto Cipola's team, SegNet, that allows to generate semantic segmentations with suitably trained deep networks, but completely different things, like we showed in NeurIP 16, that you can do protein structure prediction with deep networks. It's like a precursor of Google's AlphaFold, if you will. and video object segmentation. There's many things, and we all know at this point there's so much you can do with deep networks. So can't we do something? And indeed, this took a little bit longer in the making, but around 2017 and 18, there was a lot of SLAM approaches that were deep learning based. That appeared to estimate camera motion 3D structure with suitably trained deep networks. But unfortunately, at least from our perspective, a lot of these initial works were not state of the art in terms of performance on how accurately can you track a camera, for example. Why that is, I don't know. This is hard to say, and it's hard to summarize for all of these works, but largely I think the challenge that people faced was just end-to-end training was maybe not feasible at the time. In goes the images and out comes the 3D world and the camera trajectory. Maybe that was a little bit too ambitious at the time. And so what we have been advocating over the last years is hybrid techniques. And the first thing we did is we looked into what can we do with deep networks where they really do well. And it turned out, and this is Kuznetsov and collaborators, 2017, that you can do depth prediction. And that we thought, wow, that's amazing that from just one image, you can predict the depths. We built up on this. This is our work from 2018. You can see it's similar, but it significantly improves the depth predictions, much more crisp depth predictions that we get. It's a technique, a network that we call StackNet, I think. But the main thing about this work in 2018, it's called DVSO, was not to do depth prediction solely, but to say we can take this depth prediction and pipe it into a SLAM pipeline. Basically saying, find a large-scale reconstruction that minimizes the classical SLAM loss function, but has an additional term that says, all the depths, the 3D points that I see should be maximally consistent with the deep network depth predictions. And once you do that, you can get very accurate. Here is the monocular DSO, there's stereo DSO. I didn't mention that, an extension of DSO to stereo that we did a few years after. And what you see is here in a monocular system, and this is classical for standard classical monocular approaches, they cannot estimate the scale. So they get very accurate reconstructions, except the scale constantly drifts. Here it's very small, here it's very big, right? It doesn't know what the scale of the world is. Turns out with the monocular approach on the right, DVSO, it's on par with stereo methods, but it only uses one camera. And it kind of hallucinates the rest by the deep network. Because these deep network depth predictions, they are metric predictions. So they're absolute scale. And so it actually can get the scale. And this was a comparison where we compared to, LSD SLAM to ORB SLAM to stereo DSO. And we found that this monocular technique actually outperforms them, even though it only uses one of the two cameras. And that kind of encouraged us to look deeper, literally. How else can you use the deep networks beyond depth prediction? You can predict relative camera motion, the pose. You can predict an uncertainty. And I'll go a bit more into detail how we do this. So given two consecutive images, IT and IT prime, we have one network that predicts depths and one network that predicts relative camera motion between the two frames. And once you have camera motion and depths, you can actually warp the two brightness images and train the whole network in a self-supervised manner using the same brightness consistency loss. If you do that, you find that brightness is actually not typically conserved, even for Lambertian worlds like this one. The brightness can vary, but you can correct for that. You can introduce an aperture correction with two parameters A and B, and you can train a network to predict these affine brightness correction that aligns the two images in terms of their brightness. And for Lambertian worlds, we find that typically does the trick. But if you take this out into the real world, then it fails because the real world, or it doesn't work so well. Because why? Because the real world is not Lambertian, because there's a lot of metallic structure or glass structures where brightness is just not fulfilled, is not preserved, right? no matter how much affine corrections you apply, you will not have brightness consistency. So we said, how can we deal with this? And this took inspiration from Alex's work on an aleatoric uncertainty. We said, can we not estimate an uncertainty that tells us for every pixel in the image, how likely is the brightness really preserved? And then we simply downweight the residuals in areas where the brightness is not preserved. And that works well. And we found it also generalizes well from one training set like Kitty to a different training set like cityscapes or other. We can actually predict which areas in the image, where will the brightness be preserved and where will it not be preserved. And it finds that on the cars, on the windows, it will typically not have brightness preservation. And so the uncertainty is high, but also in the trees upright, right, where things move, you know, it just predicts. And seemingly the network can determine, okay, this is an area where brightness is maybe not preserved. And then we can feed all of these predictions in a self-supervised manner. We can train these networks, and then we can feed them all into a SLAM pipeline, as I mentioned before. And we get a technique that uses just a single camera to predict from just the left camera. It predicts the depths for the left camera and for the right camera, and generates a very large scale reconstruction. And so what you see here is a system that is just using a single monocular camera. No inertial, no GPS, no stereo, nothing. And as you can see, there's practically no drift, especially compared to standard monocular approaches like DSO. And so we've gotten, I think, quite far on what you can achieve in terms of visual odometry from just a single camera. There's practically no drift. I mean, this is not using any kind of loop closures, etc., that you would certainly add if you have them. So we also evaluated the depth predictions. This is the depth prediction quantitative evaluation, both to different kinds of methods on Kitty and on Europe. And this is an ablation study showing kind of the precision we get compared to mono depths 2. And here you see, this is trained on Kitty, but even the depth predictions and uncertainty predictions on cityscapes are quite compelling. We then looked further into how is the visual odometry. This is typically what we care about most. And we compared here to both classical optimization methods like stereo DSO or ORB SLAM. And this monocular method actually significantly outperforms them, similar to other deep learning based techniques. In fact, we compared this monocular method to both mono inertial and stereo inertial methods, and we found it's quite on par with top stereo inertial methods, even though it only uses a single camera. All right, I think I'll have to speed up because I lost a bit of time in the beginning. The next thing is that we want to go further and train neural networks to generate a full-blown 3D world. And this is work by Felix Wimbauer, who trained a neural network that uses a set of consecutive images, and we use the trajectory from, I think, DVSO or D3VO, and then we can warp all these images, create what's called a cost volume, this brightness consistency loss that we can bring in, and have a network basically predict the depths based on that. But what's important in between, we have a module that masks out moving objects. So it's assuming a static world, but then moving objects are basically the network is trained to filter them out. And so it combines both the aggregated brightness consistency across warped frames, but also the filtering out of moving objects. And then all of these depth predictions are aggregated into a large scale reconstruction. And so what you see here is CVPR21 monorec. It's a large scale reconstruction achieved from just one single moving camera. And so it gives us a nice way to create kind of what's often now called digital twins of the Earth. It's not fully photorealistic, right? This is a point cloud visualization, and we'll see one can actually do better with kind of more sophisticated novel view synthesis approaches. But this is just visualizing the colored point cloud. And I think this gives you an impression of, can we rely on cameras instead of lidars to sense the 3D world? Because this is being generated in real time from just one camera, right? And now, sure, the point cloud precision may be higher in the LiDAR scan, but do we need that precision to see the obstacles and do autonomous driving? I think maybe not. And I think this might be sufficient in terms of the accuracy and density of 3D capture, may be sufficient for doing autonomous driving. This is another kind of parallel work, Lucas Köstler. We call it Tandem for tracking and dense mapping. It's fairly similar in spirit, but it works indoor and it also uses voxel hashing to do large scale kind of dense mapping, a technique that was published in Coral and that received the best demo award at 3DP 21. So to the last part, I've shown you now that you can do monocular depth prediction. You can feed it into SLAM approaches. But what I want to show you in the end now is that we can actually go further and go from 2.5D reconstructions of the world to full 3D reconstructions. The idea here is that we move away from monocular depth prediction and we actually predict voxel occupancy or density, a bit more in the spirit of nerves, except, you know, nerves typically need a lot of multi-view images from all around, whereas this technique, it runs on a single camera put into a car. And as you can see, we can do kind of 3D prediction that allows us to reason not only about where do the objects start, but also where do they end. Because the world we drive through is a familiar world. It's also trained in a self-supervised way by using multiple consecutive images. It can learn to reason about the extent of objects. And so you can distinguish, for example, on the top right, that there are two cars and that there is a gap in between the two cars, right? The idea is kind of visualized here schematically, and this is a work, if you're interested, Felix is going to be presenting it this week at CVPR. The idea is that it's similar to the depth prediction, but also kind of similar to nerve-like density predictions. In fact, what we do is we take this egocentric perspective, and for every pixel, we predict not the depths, but a feature vector that describes the density distribution. And so it allows you to model multiple objects that are in the line of sight. Obviously, we only see the front one, but once we learn and train with in a self-supervised way, we can learn about reasoning about how big are the objects typically. And that's and it's different from nerve in one very important aspect. Nerve actually predicts the color as well for every voxel, right? We don't do the color prediction because we believe you can read out the color from your image stream. And so we only predict the scalar density, and that means we have a much easier learning problem, and we can make this much more scalable. And as a result, we can have videos like this one, where we just have a single camera. And as you can see, this is kind of a more perspective view from the top. We can actually distinguish different objects and the extent of, here's a comparison to other competing approaches like pixel nerve or monodepth 2. Here, monodepth is obviously designed to predict the depths, so it doesn't do multiple depths prediction, but here in our approach, behind the scenes, we call it, you can actually see the extent of objects. I don't want to go too much into details. One of the biggest challenges in this work was actually to do quantitative evaluation for the real world. How accurate is the full 3D reconstruction? And so Felix put a lot of effort into tapping into LiDAR across multiple frames to get some form of ground truth of the geometry so that he could show quantitative performance. And you'll find all of that in the paper. So, and here's, very much like in nerves, you can do novel view synthesis, but what's nice is that this really works on a single monocular driving video at a very large scale. You can create novel views like these here. not just for car scenes, but also for indoor scenes. You can use this technique also to, in a similar vein as a nerve-like approaches, you can do novel view synthesis. So in some sense, this confirms that maybe we don't actually need the color in the volume, but only a density is sufficient to encode the geometry, and then we have the image input to read out the colors. So to summarize, I talked about SLAM, about large scale and direct SLAM. I talked about direct sparse odometry as well. I talked about how to leverage deep networks to boost the precision and robustness of SLAM approaches, getting just monocular cameras to a level of where state-of-the-art stereo inertial systems are, allowing us to do very large-scale mappings and, in fact, also semantic 3D mapping with a single camera. And then I showed that monoreg technique that also uses just a single camera to create large-scale reconstructions that are kind of 2.5D, so they look compelling from the viewpoints where we drove from, but you don't get the backs of the cars because you don't see them. And here in this recent work called Behind the Scenes, we are able to go to a full bird's eye kind of perspective and create not a 2.5D reconstruction, but a full 3D reconstruction from just a single monocular video. That's it, and thank you for your attention.
So yeah, I believe we have 10 minutes for questions, either from the international audience from Zoom. So if you have a question, please come up to the mic so that way the Zoom participants can also hear it. So yeah, thanks.
Do you want to come to the microphone?
Come to the microphone, please. Thank you.
Otherwise, the Zoom audience won't hear your question.
Yeah.
I'm just wondering if you think you can apply some of these techniques to satellite data. It's kind of a different problem because you only have a few images, but the problem of depth estimation, I've been trying to work on it. So do you think you could take satellite data that's taken from very far away and apply it to try and make a 3D reconstruction?
I should be honest, we have worked a lot on satellite data as well, but not with SLAM techniques and not for 3D reconstruction. This was often more on semantic scene understanding. I think what is typical here is that you would typically drive down the street, and so you see the 3D world from, you know, continuously changing vantage points. Yeah. And with satellite imagery, you always have the same distance. It's not like you're moving, but it should be doable in a way. Yeah, because if you have a video from the satellite,
like a sequence of images with different angles.
Yeah, could be doable. Yeah. Obviously, the distances are very different with satellite imagery, but yeah, I'd be very curious. You know, maybe you can reach out and we can see if this can be done. Yeah. Mm-hmm.
If you want to just like you are kind of behind the microphone, that way you can.
Thanks for the talk. You just mentioned your work at the SPO.
Mm-hmm.
So you take the depth measurement from the deep neural network, and you introduce another term in your objective function.
Yeah.
So I'll ask, how do you model the uncertainty of this text?
That's a good question. So I didn't go really into much detail of how we use these depth predictions. We actually use them in two ways. First of all, we use them for initialization. When you have a SLAM pipeline, typically you minimize a non-convex problem with some iterative algorithm, and that means you are better off with a good initialization, right? And so we use the deep network depth predictions as initialization for SLAM, for the points. But in addition, we use them in the back end, basically as a term in the loss function. And this term in the loss function basically just says it should be consistent with the depth predictions of the network. I don't know if StackNet estimates an uncertainty. I don't think it does, but if you have a deep network that predicts the depths and an uncertainty, you can obviously feed that into the loss function, right? Yeah, and basically weight the loss function according to your uncertainty estimates. And you should do that if you have them. So I don't remember if StackNet provides a depth. I don't think so. But if you have a network that has an uncertainty estimation, that will definitely help, because we can basically modulate the loss function accordingly.
So maybe you can initialize your depth filter in the function with this depth from the neural network, and then after having this.
So determine the loss function, much like with the aleatoric uncertainty, we can downweight the residuals. In a similar vein, we can downweight terms where the uncertainty is high for the depth predictions.
Okay.
Hey, great presentation.
Thank you.
So it seems like from what you've shown, a single camera for 3D scene reconstruction is quite strong.
Mhm.
But in your mind, where is the limit? Like, at what point do you need more than a single camera? Or is it just always really in for realistic purposes?
So I have to be careful because, the limits keep changing. In particular, we've been pushing the limits quite a lot as to what you can do. 5-10 years ago, I would have said you definitely need a stereo camera or something to get the scale of the world. Now I take that back. We don't need stereo if we have a deep network. One should say this all works in a man-made world, right? If I took the depth predictions into a Lego world, then, the scales would all be off, obviously, right? So there's only, the question is what generalizes and what doesn't. But typically, if I see a Mercedes in the real world, it's a real Mercedes and not a toy Mercedes, right? And so the depth predictions will likely be correct. So I think you can get very far. What are the limits? Well, cameras have notorious limits. For example, people often say, oh, how about in the dark, in low light, in bad weather conditions? I didn't talk about weather, but at Artisans, we put a lot of effort into making these things robust across seasons, across lighting, across weather conditions, and you can. And for example, DSO, we tried these approaches like the one there or this one here. We demoed them in heavy rain and it was no problem. And in fact, rain is much less of a problem to cameras than to LiDAR. If you have rain and, the LiDAR beam goes through a drop of rain, that's it. It distorts everything completely. With cameras, when the rain starts, in some sense, camera-based techniques have the same limitations that humans have, because we rely on our eyes for driving, right? And so my belief is with cameras, we should be able to do anything that humans can do.
Excellent.
Humans don't have LiDAR, right? But we can do superhuman level driving if we tap into additional sensors, be it LiDAR, radar, ultrasound, you name it, right? And we should. So if we have access to the sensors and they're not too expensive, cost is a big issue. You don't want to rely too much on high quality LiDARs because they are very expensive.
So cameras get you to human level, but go beyond that, you need even more sensory data.
You may want to use whatever sensors you can get hold of. But everyone says safety is our first priority. Yeah, but if you look behind the scenes and everyone working in startups and companies in this field working with automotive knows there is a second aspect, cost. And in the end, safety can be factored into the cost as well. And so cost plays a huge role. When we started with Daimler in 2005 on driver assistance, at the time, they put a single camera, right? And when I said, can you put a second camera? The manager said, no, it's too expensive. I don't know what that manager now says about the LiDARs or people are putting on their roofs. They cost thousands of euros. I've seen cars where just the sensory hardware is $500,000. And then I say, great, if you get that to drive autonomously, who's going to buy it? Not me, right? And so cost is a huge issue. If you want to mass produce things, then every euro counts. And this is the unfortunate truth. And then so you have to build with cheap sensors, and that's why we're pushing cameras.
Thank you.
Great. So yeah, thanks for a very nice presentation. And is there a way to put this upload or so basically in one of those you presented a way for getting post estimation between two images from like a neural network that is trained jointly with the monocular estimation.
Yeah.
And there is actually another branch of works that use like it combine post estimation with monocular depth in a bit different way. That's they do like depth estimation, and then they use the depth as additional mathematical constraint for pose and sample some take matches between the images, like the classical methods. But apart from using the 2D to 2D correspondences and their mathematical constraints, they also use the depth as for another constraint, which reduces the amount of needed points for sampling, and also gives you this scale. So it's this. Have you also compared against these methods? Are you aware of?
So I didn't go much into the literature background, but obviously deep networks to predict both depths and camera motion are quite common. There's a whole zoo of different techniques, including, for example, the team of Thomas Brock's had a paper called Demon Depths and Motion Network. That's essentially predicting depths and camera motion. So this is a common strategy to do this, and there are many works. I don't have a complete overview, and I'm not sure which particular works you're referring to, but maybe we can discuss it offline and I can look into this. There's, again, very different ways to tackle the problem as well. Some also with more structure for motion approaches with fundamental matrices and things like that. Yeah, and we've also looked into that, but it's a slightly different line of work.
Thanks.
You're welcome.
Thanks for the talk. And I'm interested in some techniques in the paper behind the scenes.
Mm-hmm.
And I've noticed that a distribution has been predicted based on some volume-based features.
Mm-hmm.
But from my experience, some volume-based features, extracting some volume-based features and maybe presenting them will be time-consuming. So I'm interested in the inference speed of in the behind the scenes. And can it reach the efficiency of real time, maybe in 20 to 30 FPS? That's it.
Felix, what do you say? Can this run at 30 FPS, 20 FPS?
So getting the features is not the same speed as a movement, and then so we can, I guess, vary the volume on demand. So it's much faster than fixed nerve because for all the other nerve-based methods, because the MFP is much smaller. I didn't do any specific inference test, but it's pretty fast. So I would say at least like 5 FPS and then CPU for rendering these tests.
And yeah, should I for the maybe the Zoom audience in case they didn't hear it? Yeah, so it is fairly fast, 5 FPS. You're saying, I don't remember the numbers. And one of the reasons is that compared to other volumetric approaches like NERF or pixel NERF, as I said, we only predict the density. It's a single scalar, and we don't predict color, and that allows us to get away with a much more compact kind of
Here we're talking about the relative depth, right?
No, this is absolute depth. Yeah.
Any range of error for that?
Sure, the papers have, I think I had some quantitative numbers there. Yeah, they're in the papers. Yeah. It's absolute, and it's important because it means we can get the scale of the world from a single camera. But as I said, this requires you to know the world you're looking at. And it's invariably an approach that may not be general purpose. So meaning if I train it on self-driving and then I take it out into the forest and hope that it will give me absolute depth, it works so-so. And I was actually surprised how well it generalizes to completely different environments, but there is a limit, I think, as to how far you can take this.
Cool. Well, we can thank Daniel again for that.
Thank you.
So yeah, we're now on to the final talk of the workshop.
Jamie, we can't see or hear anything on Zoom.
Is that okay?
Yeah, so if you can check the settings just in case. So yeah, video and audio. External headphones. Yeah, that should be fine.
Excellent. All right. Let's jump in.
Oh, wait, I'm not showing the screen.
I'm not. All right, that might help. Is that showing the right screen?
Yeah. Yeah, that's great.
All right, excellent. Hi, everyone. I'm really excited to talk to you today about the frontiers of embodied artificial intelligence. In particular, some new results actually that we haven't talked about from Wave that I'm really excited to share to you all. Before we begin, I wanted to talk about why I think autonomous driving is the most fascinating area for research challenges, and in particular is driving the forefront of embodied AI. If you look at the diversity of even these scenes here, the challenge is one that's really profound, having to create a generalizable, robust, embodied intelligence that can operate with the levels of trust and safety that are required to bring autonomy to the world. To do that, we need to develop systems that have the intelligence to reason about these incredibly diverse and complex machines. And there's no better way to address this problem than with machine learning. And so that's what we've really focused on at Wave, is how can we take a new approach to the autonomous driving space and focus on developing end-to-end foundation models that can bring us this level of performance and scalability. To do this, we're developing a next generation approach to autonomy, AV 2.0. And I'd just like to briefly introduce what the key features of AV 2.0. But the first one, and this is truly important if we're going to get autonomous driving to a global scale, is that these systems are able to generalize. What we mean by this is that they can quickly adapt to new places and don't require infrastructure or linearly scaling hand-engineered behavior in each new location. The second one is that we're able to operate in a very vehicle-friendly way. This means a low bill of materials cost. As Daniel described, I think cost is a real factor when it comes to developing vehicles that are viable. And so being able to operate with a camera first on a low compute and low bill of materials cost system, but more importantly, being able to integrate into vehicles in a way that doesn't require a colossus of a sensor rig on them. This makes it possible to scale and work with diverse fleets and use cases. And then the final one is that being able to build policies that are aligned with human expectations, ensuring that we can build systems that are trusted and safe. And that's really what I think foundation models give us the opportunity to do. So where are we today? Well, today we operate a fleet of both Jaguar I-Pace vehicles and these electric vans that you see here. And in terms of generalization, we've been able to show that we're able to generalize to different cities. For example, learning to drive in London. And here we've gone to over 10 different UK cities and shown that the system can drive in these environments despite never having seen them in its training set before. You can see some of the diverse environments that we're able to drive in. So here's a shot of central London, even when it snowed in December. Some of the environments that we operate in and drive are quite complex, unstructured scenes with a really high agent count of other cyclists, pedestrians, and cars as you go throughout the environment. And don't just take my word for it. We actually were fortunate enough to take Bill Gates for a ride a couple of months ago. And here you can see a video of him joining me and our safety operator Deepa for a ride through central London. We picked him up from his hotel and drove him through busy central London and even stopped off for some fish and chips along the way. The video is on YouTube if you want to check it out. And so now we're looking at how do we commercialize the system, and are excited that we've started commercial trials for last mile grocery delivery with our partners Ocado and Asda, two of the UK's biggest grocery companies, which are now operating in London. So that gives you a bit of an overview of Wave. What I want to talk to you today about is really the foundations of modern AI, and in particular, how they apply to self-driving and embodied AI. If you think about the things that have completely transformed problems like these really hard data-driven problems, if we look at image recognition, ChatGPT or image generation, or these kind of applications, these are the ones that I think are really transforming what is possible through technology. And what I'd like to do is think about what are the foundations that have made these possible, and talk to you about how they apply to embodied AI and some of the work that we are doing to pioneer that. So stepping back, the foundations that are behind many of these breakthroughs, the ones that I listed, for example, I've listed 8 factors that I'd like to run through. One of them is data and benchmarks. The interesting thing about that is if you look at the data sets that have really catalyzed many of these breakthroughs, they often are the trigger that makes these possible. In fact, interestingly, the algorithmic advances can often come 10 to 20 years prior to the breakthrough itself. Take ImageNet, for example, image recognition. This was it's considered, I think, basically solved as of 2016 or 2017. And the ImageNet data set was put out in 2011. That was really what drove a lot of this progress to solve image recognition. But the algorithms, convolutional neural nets, they've been around since 1989. So data sets are so important to being able to iterate quickly. And with that, games and simulation also play a really key role. Why is this important? Well, it lets you get a fast feedback signal and to be able to iterate quickly against, ideally at the speed of software against the problem you're working on. Self-supervised learning, being able to move away from labeled data and learn from the structure inherent in the data itself is what really allows these representations to scale. And with that, foundation models, being able to generalize and have emergent behavior that comes out from really large scale broad training. Of course, scalable compute and architectures are required, and we've seen incredible results as you increase the size of the parameters or the data or compute in your system. And then finally, multimodality and alignment with human goals. These are ones I want to talk about a bit more today, and we have some pretty exciting results to share as to why they can be profound for autonomous driving. So if all of these foundations have been what have really advanced the boundaries and broken frontiers when it comes to ChatGPT or image generation or game playing agents like AlphaGo, I want to talk about how they can be applied to embodied AI. And for me, I think embodied AI offers new opportunities to have even greater impact than these examples themselves. We live in a physical world, and of course, what sets apart the human race from other species on our planet is our ability to build tooling. And I think intelligent machines and embodied AI is going to be that next stage of tooling that lets us achieve much more agency and achieve much more with our lives. Not only that, I think embodied AI gives us an opportunity to access more data and build far greater intelligent machines. I think we're already hitting the limits of what text, video, and images are available on the internet to train these systems. And getting real life embodied systems out there will unlock that next level of data. So in today's talk, I want to talk about 3 examples of this: reinforcement for learning for autonomous driving, language meets driving, how we can bring the latest advances in large language models to the autonomous driving setting, and finally world models, and show some results that have really shocked me with how incredibly powerful they are at being able to describe our dynamic worlds. But of course, this is a workshop on monocular depth, so it would be remiss of me not to make some comments on the role of monocular depth. And I'm showing you a very early demonstration from Wave back in 2018, when we deployed a multitask convolutional neural network that was capable of segmentation, depth, and optical flow, running in real time here on one of our vehicles in Cambridge. And so what is the role of monocular depth in developing embodied AI and intelligent machines? Well, of course, this whole presentation today is all about showing that autonomous driving is possible through monocular vision. And I think we saw some fantastic results from Daniel just before, showing that you can develop really accurate and robust odometry and mapping from monocular vision. But also we want to show that that robust decision making is possible. We started off at Wave building some state-of-the-art computer vision systems. But one of the things I quickly realized was that the point of computer vision is to obtain useful information about the world from these images in order to make decisions. So the other point I'd make is that, and perhaps this might be a bit contrarian in this workshop, is that monocular vision as a task for itself, I think is not the right problem to be working on. We want to be working on the end decision-making problem, the end outcome we're after from this embodied AI system. And to that point, we would miss the advances of end-to-end deep learning if we aren't able to optimize that whole system end-to-end. And so I think monocular vision is useful as an auxiliary task to improve the efficiency of the learning and the outcomes, but not necessarily, but not to use as an outcome in itself. The thing that makes it really powerful is the fact that you can learn from geometry motion through self-supervision. These signals are inherently possible to extract from the structure of the data, and that means that we don't require labeled data to be able to scale them. That's really powerful. And so, ultimately, I think the role of monocular vision is as an auxiliary learning signal to improve the robustness and potentially have a role in the safety and validation of these embodied AI systems. So that said, let's dive in. So the first topic of the 3 is reinforcement learning for driving. And this touches on 2 of the key foundational building blocks: on games and simulation, on how do we leverage fast feedback from sim worlds, and how do we align behavior with human goals to make it trusted and safe. So we've been working on reinforcement learning systems for some time. Another early demo from our work, this is from 2018, I was showing the very first time reinforcement learning was running live on an actual vehicle. Here, this is a model-free reinforcement learning system trained with the reward of trying to drive as far as possible without any disengagement from the safety operator. And you can see when it's trained from scratch, it starts off not knowing anything about the world and trying to drive off the road straight away. But after we give it a small amount of feedback, you can see here, episode 4, then we start to evaluate it. so on the first evaluation, it tries to drive off the road. But if I fast forward, you can see it's learned to somewhat correct after a few more examples of learning, and from learning literally from demonstration, not from demonstration, sorry, from just that safety operator feedback. That's actually me in the video grabbing the wheel and intervening. From just 10 pieces of example, it can learn entirely from scratch in order to lane follow. Now, of course, this is a very simple environment, and trial and error learning like this, I can't see a way you can do this safely in the real world. And there's a massive gap between that system and the dynamic and busy cities we live in. So the question is, how do you scale it up? And that's where I really think simulation is the unlock. So what we've developed is a simulation world, Infinity, that lets us generate infinite amounts of large procedurally generated worlds. And we can use these worlds to train agent behavior with multi-agent reinforcement learning. We can do this in an incredibly efficient and effective way with distributed training with billions of agent steps running at about 700 times real time. You can read more about it in our blog, but the design principles behind this is that we want to train all of these agents independently, not only to drive with accurate and safe behavior, but we also want to train some in an adversarial fashion to be able to try and find those edge cases so we can improve the robustness of our driving system. We want to have a very simple set of rewards, so we don't hand engineer the environment, but only a handful, such as don't hit things, don't break the basic traffic rules, and then let the behavior emerge through learning. And the result is remarkable. We're able to learn some emergent behavior like this. You can see pausing and going through tight spaces, or even complex giveaway and giveaway and other interactions. All of this behavior is entirely learned from that multi-agent setting. We give these agents no prior knowledge except for that very simple reward and that environment to learn in. And all of this complex behavior emerges as a result. The result is a number of different agent behaviors across a range of desired behaviors on the spectrum, from safe and conservative driving to reckless and adversarial driving, that we can use in order to build the robustness of our embodied intelligence. Now, of course, those reinforcement learning agents were given privileged information in the simulator to learn efficiently. Now, we can distill that policy into a non-privileged agent so it can actually drive from vision input. And this is similar to the work that I've cited on the right here. But we can use that in order to create a policy that can drive from just image input. But then we need to ask the question, okay, how do we get this to the real world? And what about the domain gap? What about the domain gap from simulator to the real world? Well, interestingly, we can actually solve the domain gap the other way. What you're seeing here is a driving policy that we learned only on real world data, now driving in our simulator environment. So during training, it's never seen any simulated data, yet it's still able to drive at a highly robust manner in this world populated by those our reinforcement learning agents trained only on real world data. And so we're starting to see our ability to close that sim to real gap. And this is even accelerated by neural rendering techniques. We've brought in the latest techniques from NERF and even dynamic NERFs to be able to create and then operate our agent behavior within these photorealistic virtual environments. Ultimately, I think the opportunity here is to be able to use simulation to develop highly expressive, diverse, and robust agent behavior in a way that is far more scalable in the real world. And then by using machine learning techniques, bring this to the real world. The second piece I'd like to talk to is language meets driving, and I'm sure, like me, many of you have been blown away by what large language models have achieved this year. And at Wave, we've certainly taken notice, and for the last 18 months have been working on how we can bring language, information, and reasoning into our driving policies. Now, this is some new work we haven't actually talked about previously, so I'm excited to share it with you all today in a series of talks at CVPR today. But I think language is such a powerful, the capabilities of these language models are so incredibly powerful, and multimodality is going to play a key part in embodied intelligence. Let me explain why. Well, language models already have a huge amount of knowledge in driving. If you take, for example, ChatGPT and ask it some driving questions, such as, you're driving along a road and you ask it, what happens if a bull rolls out in front of you? What should you do next? Well, the language model correctly identifies that you should slow down and be cautious. But then if you ask it, how would this change if you're driving next to a school? It reasons that it's more likely that a child might run out after that bull. And then if you ask it, oh, is this still true if it's at midnight? The language model says, oh, actually, children aren't usually at school at midnight, so it's even less likely. And you can see this, the kind of context and reasoning that these models have is extraordinary. And if you ask another question, like what happens if you approach a T-junction and a motorbike turns up with no one on the top of it? Now, that's an example of a really out of distribution example that you'd be very hard pressed to find in your training data. Now, what ChatGPT correctly identifies is it's a rare example and you should be cautious. So it's aware of the uncertainty and the unknown of this example. I think what I take from playing around with these systems and querying them with language, querying them with driving tasks, is that they have such a deep knowledge of the open set nature of driving scenes. And there must be a way that we can leverage that information in our embodied driving AI. People often say that a picture's worth 1,000 words. I'd actually pose the opposite question, that a paragraph is worth 1,000 pictures. Let me explain. So if you take this piece of training data and look to learn to drive based on this image alone, if you want to learn that, okay, you need to stop because there's a pedestrian on the pedestrian crossing in front of you, you're approaching a T intersection, you should give way before moving in, but actually there's also a 20-mile-an-hour road sign on the left and you should change your speed. To learn all of those things just from an image alone, you would probably need gigabytes of training data, if not petabytes, to learn those facts from the images and video. What I just told you about that image, you could describe in less than a kilobyte of text. And so the point I'm trying to make is that although there's more information content in images, the signal to noise ratio, or the ability to compress the reasoning from an image or compress the reasoning from data into text is orders of magnitude more efficient than images. There's a reason why we have evolved language to communicate between our human intelligences, and it's because language is such an efficient way of conveying the signal we want to. So what we've developed is a language model that we've grounded with our driving AI. And the result is a system that allows us to connect language and driving. This is remarkable because we can actually start to look to understand the behavior of our driving AI and improve the behavior through language. And one of the ways we test that is with visual question and answering. We can ask our driving AI questions about the scene it's about to drive through. And here you can see a example question, should you proceed through this intersection? And you can see that our driving AI is able to explain, no, you shouldn't proceed because it's important to wait for the traffic signals. And it also warns around all the other agents in the scene. Well, let me show you another one. You can ask a question like, should you honk at the pedestrians crossing the road? And interestingly, the large language model can pull in information that is not present in our training data, but pull in information from the internet text that it's trained on. And then say that, no, you shouldn't honk because the traffic light's red and they're actually doing the right thing. Now, this is remarkable because it's showing that we can bring in the information from the internet, from language, and use this to improve and understand our driving AI. Now, what does this look like if you actually go for a drive and prompt the driving AI to actually explain how it's doing? Well, you can see here at the bottom, it's describing the things it's doing as it's driving here. It's turning, it's making a turn to follow the route, it's maintaining its speed, then it's slowing down, and it even explains that it's stopping based on pedestrians at the crossing. Let me show you another example. So we're driving because the road remains clear, but we're slowing down because there's a cyclist, that there's pedestrians at the zebra crossing. And you can see that this shows that there is some inherent language understanding of the driving scenes it's pretty remarkable driving around and querying the AI and asking it questions around what it thinks about various things. But here you can see it's even identifying that it's taking a lane change to be able to follow the intended route. This is the beauty of taking this foundation model approach to autonomous driving, is it lets you bring in language information. And I think this provides an extraordinary opportunity for embodied AI. Clearly, there's huge opportunity from here. We should be thinking about how do we ground vision, language, and action together. Today we're capable of asking our driving AI to explain to us why it's driving. We're very close, and I think not far away from being able to go the other way, to be able to prompt our driving AI to make certain decisions based on text input. I think this provides an extraordinary opportunity around things like perhaps remote assistance, where if the vehicle gets stuck and needs to ask for help, we can provide it with that help through a text prompt. Or for interpretability of the system, to be able to actually have the system explain to us what and why it's doing certain things. Language provides such a strong ability to be able to interact with the driving AI, just like it provides us ability to interact between our human intelligence, between each of us. So if that wasn't exciting enough, let me build on that and show you some of the new work we've just developed around world modeling. And in particular, I'd like to talk about Gaia-1, a world model that we just released a couple of days ago, and we're talking about here at CVPR. Now, world modeling touches on every single one of these foundations. It's, to build a world model is truly, if you have a world model, you truly have an understanding of the world. And I would argue that is a prediction model, a world model, a general purpose prediction model is the closest definition to AGI that I can think of. Now, here we're looking at a narrow world model, a world model that can particularly understand driving scenes. And I mean, it's very easy to motivate why this is important. If you take this top image and ask the question, should you keep driving? It's really hard to tell the answer. But when you start to bring in a video and start to predict the dynamics of the scene, you can tell that it's safe and this car, that white car on the left is actually stationary. So understanding dynamics and motion and being able to predict behavior is fundamentally important to safe and trusted behavior in our dynamic worlds. What is a world model? Well, we define a world model as a generative model that predicts what happens next, conditioned on action or some prompt. So it's a model that can predict the next state given our current state and an action. Why is it important? Well, besides from if you have this, you truly have a system that can understand the world, but it also gives you a fully learned and dynamic simulator. It gives you the ability to ask what ifs and counterfactually reason about scenarios. It lets you unlock model-based reinforcement learning and imitation learning because you can use this as a simulator to actually play and interact with the world, or even explore search-based methods where you might online want to explore how your action is going to affect the world for the next few steps. World models have been talked a lot about in the field of machine learning and in particular agent learning. Some of the papers I've been inspired by are these, such as World Models by David Haar and Schmidt-Schuber a couple of years ago, or the Dreamer V2 system that expanded and scaled up some of these results. And more recently, I really enjoyed Jan LeCun's review paper or positioning paper where he talks about the importance of world modeling to create intelligent machines, and in particular, how it is the most important building block to advance towards embodied AI. And we've been working on this for a while at Wave as well, even since the very beginning in 2018. We actually started off by developing and adapting a system very similar to that Dreamer V2 citation I shared earlier to put that on the road. And when we were exploring very early algorithms on that quiet country road I showed where we learned to drive with reinforcement learning, that was a model-free reinforcement learning system. We also approached the problem through model-based reinforcement learning. And to do that, we learned a world model that could, you can see on the right here, predict how things would unfold on that country road's driving scene. And the result was a system that could drive on that road despite never having experienced it before. So this driving policy was entirely trained through the world model. It had never experienced any on-policy interaction of the world. So we were able to show that in 2018. But of course, again, it's a very limited setting and limited environment. Since then, we've been scaling up our world modeling. but largely through offline results. So we had a result some of our colleagues worked on called Fiery, which was all about future prediction using bird's eye view, and that was followed up by Mile that actually connected it with an imitation learning policy. But some of the limitations of these work is we only really showed results in simulation. It required a bird's eye view and quite a large amount of semantic labels. I mentioned one of the foundations of modern AI has been self-supervised learning, and one of the key breakthroughs that enables the results I'm about to show today has been advancing this work from a supervised, label-driven method into a self-supervised vision-based approach. If you want to read about some of the building blocks to the system, though, from the Mile work, the architecture here, but it's essentially a recurrent approach that compresses the state into a bird's eye view latent representation and can unfold it there, decoding at each time step into outputs like the semantic segmentation or the actions. Before I share our latest world model results, just to talk about some other work around the work that we're doing, because of course this is a really exciting area of research, and there's many other folks that have built really important systems along the development of world modeling. We've had systems like NVIDIA DriveGAN, diffusion modeling of videos at various levels of accuracy and robustness. We've also seen higher level systems of high level accuracy like Gen 2 from Runway, which is really incredible at generating videos that are ultra realistic. Although I have shown one here of someone walking backwards. They have much better examples if you want to go and look at Runway. But the point I was going to make here is that these systems are video generative AI systems. They're not conditioned on action. They're not a world model that allows you to actually drive and interact in that world. They are video generative models that are simply generating the future video. World modeling and the power of all the opportunities I described before about being able to learn and interact in this world requires you to action condition it. And that's what we've built with Gaia 1. Today, we're announcing Gaia 1, which is a generative AI for autonomy. And the results are remarkable. You remember that first video I showed you at the very beginning of this presentation? Well, the thing I'd like to tell you now is they weren't real driving videos. The opening slide I shared today and this slide here, these are all videos generated through Gaia 1. If you look at the diversity and that these results, they've blown me away. And we've only had access to this model for a couple of weeks, but every day we explore it, we discover new things from the model. And I want to show you some of the results, including some that we even found out just yesterday. So what are the properties of Gaia 1? Well, Gaia 1 is a world model that's self-supervised, so it doesn't require labeled training data. It's an auto-regressive model, as you might expect, that's able to regress the future. It's capable of being conditioned not just on video and action, but also text. It's temporally coherent and able to imagine very long sequences. We can generate up to minutes of driving. And here you can see an example. This is all generated through Gaia 1. We are driving in a virtual world, and this entire sequence is being generated from this world model. I've never seen anything like it, and I think this is unlocking so many possibilities for autonomous driving. So as you might expect, the architecture itself is as I said, it's an autoregressive world model. We're able to take inputs from text, video, and actions, encode them into tokens, and then feed them into that world model that can auto-regress states and before decoding to the video output to show some of the examples that I'm sharing here. So to show you some more examples, the diversity, the ability to model pedestrians, vehicle behavior, and even learn a policy that can interact within this world that's realistic, that's diverse, and that's ultimately safe. These are some of the results that we see emerge from this training, which are truly remarkable. We can look at diverse futures. So this is the world model being prompted from the same video input. And you can see that multiple different video sequences are being generated from here, showing the diverse futures. It's able to show quite multimodal behavior. And you can see these futures, as they play forward, diverge quite significantly into the future. Here you can see another one where we're turning a corner, and you can see that it's able to imagine and ultimately, imagine different futures that might play out, which lets you explore and understand the uncertain future of what might actually eventuate. I mentioned we can action condition it, and this is so important to be able to learn and drive within the world. So here you can see, a couple of seconds into this video, we start action conditioning it on different actions. You can see from turning left to right, and you can see that the world model responds accordingly, generating a future that's conditioned on the action that we apply into it. Now, this is even more remarkable. Here, we're action conditioning it on this is a manually chosen, just a zigzagging action. We're basically driving with a sinusoid input function. And you can see that not only is it being action conditioned and driving in quite a remarkably temporally consistent manner, but even look at this, is that as it drives around this, the world it's generating is consistent. You can see that the objects, even the thin structures, are consistent as we drive throughout the world. And it is, I can show you another example, which let me point out some things that you might notice as you stare at this one. Again, this is a long sequence where we're putting in a manual zigzagging path, but you can see here we're action conditioning. It's driving quite far out of distribution. We have no training data in the bush, and you can see it's rendering and imagining driving into the bush in a very realistic manner. Now, I'd ask you to take a look at, as we drive, you're going to see a very thin structure in the distance. If I pause the video, in fact, do you see the structure here? You can see it's very thin, maybe 1 pixel wide structure in the distance. Even look at that. It's able to be kept in a temporally consistent manner. As we zigzag back and forth, it retains that structure. So what we're seeing is that this world model is built this embodied structure of the world, and it's built some representation that compresses so many different concepts and behaviors. Truly, I think we're seeing some emergent properties of this compressed world, that it's representing structures that are consistent and behaviors that are incredibly diverse. And those are just some examples. Let me show you some more. So I've shown you that we've been able to condition it on video prompts, on action prompts. Now we're conditioning it on text prompts. So here we've fed in the same video input, and we've given it a different prompt, one to turn left and one to turn right. And you can see that our system our world model is then driving and making a left and right turn that's obeying that text prompt. This one's even more interesting because we don't put in a video prompt here. This is entirely generated from scratch with just the text prompt going around a stop bus. So we've taken we've taken that prompt with no action or video input, and it's generated this sequence entirely from that text prompt alone. Here's another example where we feed in a video prompt, but then give it different text prompts to condition on it. And you can see that it's again able to simulate various counterfactual examples in this driving scene. Another one, control the time of day. You can see that we can prompt it halfway through this video. We inject a prompt and ask the world model to start simulate nighttime driving. It's been able to change the time of day and even simulate us going from looks like a rainy daylight scene into a nighttime scene. So those are just some examples of what we've seen after a few weeks playing with this world model. So what's next? Well, just like the GPT series saw compounding improvements of scale, we see the exact same response. The model I just showed you is less than 1 billion parameters, and we're about to hit go on a multi-billion parameter version of Gaia, and we expect to see even more richness, robustness, and improvements based on scale. But more importantly, we're excited to be taking this world model as a foundation model and integrating it into our autonomous driving to improve the robustness, to be able to learn from diverse and counterfactual experiences, and ultimately build a safer and a more reliable embodied AI. So let me sum up. So today I've talked to you about some of the new results that we've developed at Wave, but the key takeaway, which we're living and breathing every day, is that autonomous driving is an embodied AI problem. And if you look at the foundations that I talked through that have really catalyzed the modern AI development, we believe that the same foundations will be what creates breakthroughs for self-driving and embodied AI too. That's why we've made such key investments in being able to push the state of the art of these foundations in the embodied AI space. And in particular, when you go beyond thinking about self-driving as a perception or a supervised policy learning problem, it opens up so many possibilities, such as world modeling and multimodality through language, that I truly believe are going to provide step change capabilities for embodied intelligence. So thanks very much for inviting me to talk here today. Let me sum up. We are absolutely looking to double down and grow our efforts. So if this is interesting to you, we are hiring and growing our team. So please do reach out or come chat to some of our team who are here. We'd love to have a conversation. And if you have any questions, feel free to get in touch. My contact details at the bottom. But thanks very much, everyone. I'm glad to take any questions.
Yeah, again, so we have time for questions. So if you line up at the microphone, just so we can start getting the queue done. But yeah, thanks.
Thank you so much for the great talk. I have one question. So one of your core messages of the talk was to integrate foundation models into autonomous driving. However, autonomous driving is really requiring us to do real-time control. So I was wondering whether you could comment on that, on where to introduce foundation models in the control stack.
So I think there are two opportunities here, right? There's training and test time to leverage this kind of technology. At training time, of course, you don't have the real-time constraint and you can run slower than real-time models to generate data or to explore solutions. That, of course, is a big opportunity, but let me park that one and address the online side of things. So there, of course, today we can't run a 175 billion parameter GPT-3 plus system in real time on the car today, but we can run a 1 to 10 billion parameter model. And those models are still exceptionally powerful. We are also seeing advances, even month on month at the moment, of being able to take results that you see previously with hundreds of billions of parameters and actually get them with 30 billion parameters. And so I think the trends we're seeing in improvements to compute and driving down the computational cost of some of these large foundation models will play in the favor of these methods. But yeah, ultimately there is a compute bound. What I would say though is within that compute bound, there is an awful lot that we can exploit with foundation models.
Really nice presentation, Alex. I have a question also regarding the language models being introduced in driving. ChatGPT has been criticized that every now and then it just makes statements that are just plain false. I think for ChatGPT that may be okay, but once you introduce that as a machinery in a safety critical system like a self-driving car, I could see issues. How can you guarantee that the language models will not say something that will completely deteriorate the performance?
Great question, Daniel. So hallucinations are a big challenge in language models today. I think there's three things that we need to think about, though, to overcome these challenges. So the first one is the way that the language space is dealing with hallucinations right now is with a brute force approach, right? More data, you drive down the hallucinations, and I expect they'll asymptote somewhere that hopefully is acceptable to you if you're building that use case. So brute force is certainly the way the industry is taking it today. And with more data, we will expect these to improve. But that's not enough. And I think certainly, as you point out, autonomous driving as a safety critical use case, we need to be aware of what the model does and doesn't know. And this is where I think being aware of the model's uncertainty is hugely important. One of the interesting things with the language models is you even saw some of the examples I gave. They were aware when scenarios were weird or out of distribution. And I'd find it hard pressed to see a model trained on a computer vision data set to understand the open set nature of the world like these language models do. So I think they provide a really great platform to be able to build uncertainty estimation techniques and even ensuring that you understand what they don't know. And then the third one I'd say is that, of course, brute force is not enough, and I expect other methods to overcome hallucinations, whether this is structures that better create implicit structures to give rise to more causal reasoning, or even things like world modeling that let you explicitly understand the implication of your decisions, I think algorithmic advances will play a big manner too. So I agree it's a problem, but it's one that I think can be addressed either by brute force scale, by awareness of uncertainty, or algorithmic advances with things like world models.
Yeah, that's really nice presentation. Yeah, thanks for that. I had one generic question and very specific question, but the generic one is, given the simulation models, one of the core criticism of the simulation models are around the prediction of the behavior of other pedestrians or other vehicles. With language models, is there any jump and improvement of the simulations, given we can feed in much more simulated text and use some kind of an common encoding space to generate these from the other side? Like, has there been an improvement in that? And this very specific question is, can we use the language text which has been trained specifically for these kind of data sets to predict about what to do next when the model is underconfident, like you were saying with respect to this, like it was generating good captions, which was very good. Can we, instead of relying on a human to prompt it when it is underconfident, is there a way we can train an independent off-the-shelf language model which can run at that time and then like feed in a specific input?
Yeah, those are great questions. To the first one, we haven't yet brought language capabilities into our simulation agents yet, but I would expect to see some of the same improvements we see with on-road agents there too. That's, with simulation, the challenge there though is that you have a much more significant cost bottleneck because you need to run it at a much larger scale. So that's something that we're working on, but we don't yet have results to talk about. On your second question around using these models to, I guess, create an active learning loop, 100%. I think that's the way that we're going to overcome edge cases at scale, is having a self-supervised or automatic way to find the challenging scenarios. I think language gives a great opportunity there to explain and actually teach the model to explain to you when it doesn't understand a scenario, or looking at other things like you can look at the uncertainty in the world model, or perhaps the entropy of the futures it generates. If you sample 10 futures and they're wildly different, it's an uncertain scenario. If you sample 10 and they're all the same thing, then maybe you've got that covered. I think there's many different methods, and Daniel talked about some other uncertainty estimation methods, including some of the ones I worked on in my PhD, which I'm sure are very outdated now. But some of those family of methods to drive a data learning loop, I think, is the key to overcoming problems at scale.
Thank you.
Thank you.
Hello. I think the generative AI was very interesting. I was wondering if it kept information about what it has already generated. So, for example, if you ask it to look into place, does it keep information? And the other way, for models that try, the reinforcement learning models that try to predict what to do when driving, if something goes out of scope and they don't see it anymore, do they still take it into account? For example, you have, I don't know, a cyclist that's going. So weird situation, but like a cyclist going in a loop, and he should come back into your field of view, but you don't see him. Do you still take it into account when predicting what you're going to do?
That's where I think bringing the world model into our driving agent is going to give us those capabilities. In order to reason about that, you either need some explicit occupancy method, like the ones that Daniel was talking about before, or an ability to predict and reason about these systems. And we've taken the path of being able to build a world model that can predict those things. And so if the world model in its state has the signal where it's seen that cyclist, it should be able to predict, there's an uncertain future. It might turn back and it might not, but it should be able to understand that distribution.
And so for the generative AI here, if you ask it to go in a loop, does it keep information about what it has already done or not? Like if you go left and then you tell it to go back, right?
It's designed to. So as for the specific example, it would depend on how good the signal is and how effective the world model is for that problem. But that's the problem it's designed to exactly solve.
Okay.
We would need to test it to see for the specific example, but yes.
Okay, all right. Thank you.
Thanks.
Okay, so yeah, thanks for the presentation. And I would like to ask you, if you took one of the Jaguars to Vancouver or to some other place which drives on the right, what do you think would happen?
I think which side of the road you drive on is a pretty easy behavior to learn. And I expect a small amount of data here, we'd be able to condition the model to drive on that side of the road. I think the more interesting challenge would be things like four-way stop signs, or I don't know if you have this in Canada, but in the US, like right turn on red, some of these kind of behaviors that we don't have in the UK. Ultimately, though, I think driving behaviors and cultures and rules that are localized should be able to be learned. It won't take 100% of the training data to relearn. It'll be a very small fraction, but I think learning on an increasingly large data set that covers more and more geographies, we should be able to build a model that can adhere to the local behaviors through a localized prompt. We prompt the model saying, you're in Canada, drive with Canadian culture, versus you're in the UK. And as long as it's got that in its training data, I would expect it to learn those behaviors.
And for this, you need the driver to first like steer the car to the right, or it will steer there on its own?
I would expect we need to get a small seed amount of training data from that environment to be able to learn the behavior. So, if we had X amount of data in the UK, I think 0.1 or 0.01x of that data in Canada, we should be able to take that learned foundational model approach and adapt it to an environment like Canada.
Okay.
I look forward to bringing our cars here.
Great, thanks.
Cheers.
So I guess that's everything. So yeah, thanks again. So yeah, I guess just before everyone leaves, just wanted to say thank you again for all everyone for attending. Obviously, thanks to all the speakers. There were some amazing keynotes, and of course, yeah, thanks to all the participants in the challenge. And yeah, again, as I was saying during my talk, we are looking for people that might be interested in helping organize future editions. So if you're interested or know someone who might be, then reach out, and yeah, would be happy to talk about that. But yeah, again, thanks everyone for coming.
Thanks, Jamie.
Thanks.
Good job.